It's easy to see a headline like James Webb just found something older than the Big Bang and feel like the entire universe just glitched. If something is older than the Big Bang, that would mean it existed before space, before time, before the laws of physics even clicked on. The idea sounds dramatic, but what Webb is actually showing us is a lot more grounded and honestly, a lot more interesting. The Big Bang isn't just a moment when stuff exploded, it's the moment when the clock started. So when people say Webb found something older, what they usually mean is that it found something earlier than we expected. Something that formed surprisingly fast, surprisingly bright, or surprisingly massive in a universe that was still basically a newborn. Webb is picking up light that left distant galaxies more than 13 billion years ago. By the time it gets here, it's stretched and faint, but it carries a snapshot of what the universe looked like just a few 100 million years after everything began. And some of those snapshots don't match what our models predicted. So in this episode, we're going to clear up the confusion. We'll look at what old actually means in cosmology, why Webb's discoveries are causing so much debate, and how these early galaxies are forcing scientists to rethink how fast the universe built its first structures. No sensational claims, just the real story behind why Webb keeps surprising the people who thought they already knew how the early universe worked. When people hear Big Bang, the mental image is usually something like a giant firework going off in empty space. But that picture is misleading, and it sets people up to misunderstand everything that comes after. The Big Bang isn't an explosion in space. It's the point where space itself begins to stretch, expand and cool. Before that moment, there isn't a background you could float in, no dark void waiting to be filled, no cosmic scenery. There's no outside to blow into. What we call the Big Bang is simply the beginning of the physical conditions that allow anything to exist in a measurable way. Think of it this way. If time is like the timeline in a movie, the Big Bang is frame zero. You can't go to a frame before the movie starts because the film hasn't been recorded yet. You can try to imagine what happened before, but any answer you give wouldn't be part of the movie anymore. Cosmology has that same limitation. When scientists talk about the age of something in the universe, they're always referring to how long it's existed within the movie, within the timeline that starts at the Big Bang. That's why claims about Webb finding something older than the Big Bang don't make sense physically. If an object truly had an age greater than about 13.8 billion years, that would mean it somehow existed before the very conditions that define age. It would mean time didn't start when we thought it did, or that time works differently than every observation we've made suggests. Those are huge, multi-billion-dollar questions that you don't settle with a single telescope snapshot. But to understand why this matters, you have to get a clearer picture of what the early universe actually was. In the first fraction of a second, much less than a blink, the universe was a hot, dense environment where energy and matter were almost interchangeable. There were no atoms yet, no stars, no galaxies, not even particles like electrons in the form we're familiar with. The universe at that point was closer to a rapid, chaotic rearrangement of raw energy than anything we'd recognize as stuff. And because everything was so tightly packed, the idea of location didn't have the meaning it has now. You couldn't point and say, this part is over here and that part is over there, because the distances we use to anchor those words didn't exist. As the universe expanded, it cooled enough for the first particles to form. This wasn't a gentle process. The early seconds were dominated by collisions, annihilations, and transitions between high-energy states. It took a few minutes for the lightest atomic nuclei to stabilize. It took hundreds of thousands of years for electrons to settle into orbit around nuclei, finally creating neutral atoms. And it took hundreds of millions of years for gravity to gather enough of that matter into the first stars and galaxies. All of this means that when we look at the earliest objects Webb has found, we're not looking at anything that formed right after the Big Bang. We're looking at structures that took time to develop in a universe that was still young and changing rapidly. This timeline is important because it sets a limit on how old anything can actually be. If the universe became transparent around 380,000 years after the Big Bang, the moment when photons could finally move freely, then the earliest possible light we can detect comes from that stage. And since the first stars didn't ignite until tens or hundreds of millions of years later, any galaxy we observe must fall somewhere after that. Nothing can shortcut this sequence because these steps weren't optional. They were simply the conditions the universe had to go through before anything like a star or galaxy could exist. Even the method we use to measure cosmic ages depends on this chronology. Distances in cosmology are tied to how long light has been traveling. When we say something is 13.4 billion light-years away, we're saying the light left that object 13.4 billion years ago and has been stretching on its way to us as the universe expanded. That stretching affects the color of the light, which lets astronomers calculate its redshift and convert that into a rough time when the light was emitted. Webb is built to measure that infrared shifted light with more precision than any telescope before it, which is why it keeps revealing galaxies at earlier and earlier times. But here's the catch. Seeing something earlier doesn't mean the object is older. If you look at an old photograph of yourself, the picture shows you at the age you were then, not the age you are now. Webb's view of early galaxies works the same way. The universe today is 13.8 billion years old. If Webb sees a galaxy as it was 300 million years after the Big Bang, that galaxy today is also 13.8 billion years old minus whatever age it formed at. The snapshot is young, not the object itself. This distinction is where a lot of the confusion comes from. People hear oldest galaxy and assume it means older than the universe, when in reality it's oldest snapshot of a galaxy we've ever captured. Another key point is that cosmic age isn't measured by counting years the way we count our birthdays. It's measured by fitting all observable data into a model of how the universe expands. This model is supported by several independent lines of evidence: the cosmic microwave background, the abundance of light elements, and the distribution of galaxies on large scales. All of these pieces fit together in a consistent timeline. If something truly defied the Big Bang's age, it wouldn't just be a strange galaxy, it would break the entire network of observational evidence. That's part of why scientists are cautious. When Webb picks up something surprising, the first question researchers ask isn't, is this older than the Big Bang? It's, is our interpretation correct? Maybe the redshift was miscalculated. Maybe the object has a different composition. Maybe what looks like a galaxy is actually several objects overlapping in the image. There's a whole checklist of possibilities that gets sorted through long before anyone suggests rewriting fundamental physics. There's also the question of what time means in a universe that is expanding. Time isn't the same everywhere. Gravity, motion, and the distribution of matter all influence how clocks tick. If you put a clock near a massive object, it runs slower. If you move quickly relative to someone else, your sense of time stretches compared to theirs. On cosmic scales, the expansion of the universe shapes how we define time in the first place. So when we say the universe is 13.8 billion years old, that number is already the result of converting cosmic time into something that makes sense for observers like us, sitting on a planet orbiting a star in a galaxy billions of years removed from those early conditions. If you ever hear someone argue that something doesn't add up, it's often because they're mixing together everyday time with cosmological time, which aren't interchangeable. Another layer that people miss is that the Big Bang isn't an event that happened in a single spot. It happened everywhere at once. Every point in space today can trace its existence back to the same origin, so there's no location where something could pre-exist the event. That's why scientists don't ask whether an object is older than the Big Bang. Instead, they ask whether the models describing the universe's early growth are missing something. Maybe the first stars formed faster than expected. Maybe black holes grew more efficiently than simulations predicted. These are questions about how quickly the universe organized itself, not about whether it existed before it existed. With that in mind, the Big Bang isn't a fragile idea that collapses the moment a telescope finds something bright at high redshift. It's a framework built from decades of observations, each one independently pointing to the same origin. You can challenge the details of early galaxy formation without challenging the entire foundation. In fact, refining those details is exactly what new telescopes are supposed to do. Science doesn't stand still. It updates as better data comes in. That's the context missing from the dramatic headlines. When Webb finds a galaxy that appears surprisingly mature very early on, it's not breaking the Big Bang. It's revealing that the early universe was more efficient, more active, or more complicated than we thought. The discovery forces scientists to revisit the models, adjust the initial conditions, or consider new pathways for star and galaxy formation. None of that threatens the age of the universe itself. It just means the universe used its time differently than our models predicted. So when you hear someone say Webb discovered something older than the Big Bang, what's usually happening is that they're collapsing all of these ideas. the age of the universe, the speed of early structure formation, the meaning of redshift, and the concept of cosmic time into one oversimplified idea. And when you untangle those concepts, the misunderstanding falls apart. The universe isn't being contradicted, it's being clarified. Webb is doing exactly what it was built to do: reveal details that help us refine our picture of how everything came to be. If you want to understand why Webb keeps revealing earlier and earlier snapshots of the universe, you have to understand what makes it different from every telescope that came before it. Webb isn't just a bigger version of Hubble. It's built around a completely different idea of how to capture ancient light. Light that has been stretched, dimmed, and distorted by more than 13 billion years of cosmic expansion. The reason Webb can see objects from such an early era is that it doesn't try to chase the universe with visible light. It goes after the light that has been pushed into the infrared, the part of the spectrum where the earliest galaxies now glow after traveling such an enormous distance. To see why this matters, imagine shining a flashlight through a thick fog. The blue and violet parts of the beam scatter almost immediately, while the longer red wavelengths pass farther before they fade. Space behaves a little like that, except instead of fog, the culprit is expansion. As the universe stretches, every photon stretches with it. A photon that left a star burning with a bright blue-white shine might arrive here as a deep red glow, or even farther into infrared wavelengths that our eyes can't detect at all. Over billions of years, the expansion doesn't just change the color of the light, it also spreads it out so much that capturing those photons becomes almost impossible without a telescope designed to be ridiculously sensitive. That's why Hubble could only get so far. Hubble sees mostly visible light with a bit of coverage near the infrared. Webb was built from the ground up to dominate that entire infrared range. Even the decision to put Webb 1 million miles away from Earth has everything to do with this. Earth is warm, and warm things emit infrared light. If Webb were close to Earth, it would be surrounded by infrared noise. The telescope's detectors would be flooded with heat signals from our planet, from the Moon, from the telescope itself, and even from the Sun. So the engineers placed Webb at a stable point in space where the Sun, Earth, and Moon all sit on the same side of the telescope. Then they built a giant sun shield to keep the hardware cold enough that its own heat doesn't interfere with the faint signals it's trying to detect. The sun shield is basically a giant umbrella that drops the telescope's temperature so low that any infrared light Webb sees is coming from the universe, not from the telescope. That temperature difference is crucial because the earliest galaxies don't shine with the kind of intense brightness we're used to from nearby stars. A galaxy only a few 100 million years after the Big Bang hasn't had time to produce a long chain of generations of stars. Its light is a mix of young, hot stars and the surrounding gas, excited by those stars. Over billions of years of travel, that light has stretched into wavelengths far outside the visible range. If you pointed a normal telescope at these objects, you'd just get darkness. Webb sees what looks invisible to almost everything else. The telescope's mirror design also plays a huge role. Webb uses a segmented mirror made of gold-coated beryllium. The gold isn't for decoration, it boosts the mirror's reflectivity in the infrared. And the mirror's size lets it collect more photons in less time. When you're dealing with light that left its source when the universe was younger than a toddler, every photon counts. A smaller mirror wouldn't collect enough to tell you anything meaningful. Webb's designers spent decades perfecting a mirror that unfolds in space, aligns itself down to nanometer precision, and holds that shape despite temperature swings that would warp most materials. The next trick is how Webb actually interprets the light. It doesn't just take pretty pictures. It breaks the incoming light into spectra, basically stretching it out into a rainbow so faint and so detailed that it can reveal what elements are present, how fast the object is moving away, how old the stars might be, and how much dust sits between us and the source. This is how astronomers measure redshift accurately. The more the spectral lines shift toward longer wavelengths, the farther away and earlier the object is. When Webb confirms redshifts of 12, 13, 14 and beyond, it's using spectroscopy, not guesswork. This is why its discoveries carry so much weight. Anyone can see a smudge in an image and declare it a distant galaxy, but only precise spectroscopy can tell you whether that smudge truly comes from the first few 100 million years of cosmic history. Another reason Webb can see so far back is something called gravitational lensing. Massive clusters of galaxies can warp the fabric of space-time enough that light from more distant objects behind them gets stretched and magnified, almost like a natural telescope built into the universe. Webb can take advantage of these cosmic lenses by pointing at known massive clusters and capturing the magnified background galaxies. This technique lets it see objects even fainter than its already powerful instruments allow. When you hear about galaxies at record-breaking distances, lensing often plays a part. It's the universe helping Webb push beyond its natural limits. But even with all these advantages, the earliest light isn't easy to interpret. The signals are weak, the objects are tiny, and the backgrounds are full of noise. Webb's instruments have to subtract out contamination from closer galaxies, cosmic rays, stray light, and even detector quirks. Each observation goes through layers of processing before astronomers can say with confidence what they're looking at. There's a reason early claims sometimes get revised. A faint, faraway galaxy can initially look like it comes from an extremely early time, only for later spectroscopy to reveal that it's actually a dusty galaxy from a more recent era. Webb's ability to capture the faintest infrared light ever detected doesn't eliminate the need for careful analysis. It just gives scientists much better starting material. Understanding how Webb sees the early universe also requires understanding what early universe actually means. When astronomers talk about the first few 100 million years, they're talking about a time when the universe was still filled with neutral hydrogen gas. This gas absorbs ultraviolet light, creating what's called the Lyman break. As the universe expands, that break shifts into the infrared. Webb uses this shift to identify candidate early galaxies. If the break appears at certain infrared wavelengths, it suggests the object is incredibly distant. But this method alone can't confirm the distance. Only spectroscopy can do that with certainty. This is why Webb's spectrometers, NIRSPEC and NIRCAM, are just as important as the giant mirror. Webb also uses something called deep field imaging, where it stares at the same patch of sky for tens of hours to collect enough light to reveal objects that would otherwise be invisible. These deep fields show galaxies that are extremely faint and extremely small, sometimes just a handful of pixels across. But those few pixels carry information from the universe when it was still getting its act together. Hubble's deep fields were groundbreaking, but Webb's infrared sensitivity lets it push the frontier even farther. The difference isn't just a step forward, it's a leap into a part of the universe no one could reach before. Another subtle but important detail is that Webb isn't just looking for light from stars. It can also detect emission from ionized gas, warm dust, and the interstellar medium of early galaxies. This helps astronomers reconstruct what conditions those galaxies formed under. In the early universe, stars were more massive, more volatile, and shorter-lived. Their ultraviolet radiation ionized the surrounding gas, which then emitted infrared signatures as it cooled. Webb's instruments are tuned to catch these signatures, which means it can detect galaxies even before they have well-formed stars. In some cases, Webb might be observing light from the very first waves of star formation, not from mature galaxies. That's something no previous telescope could do at this level of detail. The telescope also has the ability to separate light based on location within a galaxy. This means it can study how star formation varies across different parts of early galaxies, even when those galaxies are just tiny smudges in the image. By mapping out where the light is strongest, astronomers can infer how these galaxies grew, how quickly they formed stars, and whether they were undergoing bursts of activity, or slow, steady growth. This level of detail lets scientists compare early galaxies to modern ones and see just how different the universe was in its first few 100 million years. One important point is that Webb doesn't just show us earlier times, it shows us unfamiliar conditions. The early universe wasn't simply a younger version of today's universe. It was a place with different chemistry, different radiation levels, and different gravitational environments. Stars formed from almost pure hydrogen and helium, without the heavier elements that help modern stars cool and collapse efficiently. This means early stars could grow enormous, sometimes hundreds of times the mass of the Sun, before burning out quickly. Webb's ability to detect the signatures of these massive early stars helps scientists understand how the first galaxies assembled so quickly. When people wonder why Webb is finding bright, surprisingly large galaxies so soon after the Big Bang, part of the answer is that early stars were simply different. Webb is tuned to detect the kinds of light those stars produced even after billions of years of redshifting. All of these capabilities, infrared sensitivity, cold operation, segmented mirrors, spectroscopy, gravitational lensing, deep fields, work together to let Webb see the universe in a way that finally matches the scale of the questions scientists have been trying to answer for decades. Without these, the early universe would still be a blurry, underexposed mystery. With them, we can now look back far enough to watch the cosmic dawn unfold in real data instead of theoretical reconstructions. What makes this especially interesting is that Webb isn't hitting a limit yet. Every new deep field, every new lensing study, every long stare into a quiet patch of sky increases the chances of catching even earlier structures. The telescope is still in its early years of operation, and scientists are already revising their assumptions about how fast galaxies formed, how quickly stars ignited, and how efficiently matter clumped together in those first eras. The surprises keep coming not because the Big Bang is wrong, but because the universe is showing us details we never had the tools to see before. When scientists call something the oldest galaxy ever observed, they're not saying that the object is somehow older than the universe, or older than the Big Bang. They're talking about the earliest snapshot we currently have of a galaxy in the cosmic timeline. It's similar to finding your oldest childhood photo. You aren't older in the photo than you are today. The photo is just from an earlier moment in your life. Astronomical observations work exactly the same way, except the photos come in the form of ancient light that's been caught after traveling across billions of years of expanding space. The key to understanding this is that age in astronomy is always tied to when light left the object, not what the object would be if you could teleport to it today. That difference seems subtle, but it completely changes how headlines like "oldest galaxy" should be interpreted. Imagine standing on a beach at night, looking at a lighthouse 10 miles away. The light you're seeing didn't leave the lighthouse at the same moment you're seeing it. It left seconds earlier. In our everyday lives, that delay doesn't matter, but on cosmic scales, those delays stretch into billions of years. And because light is our only messenger from those remote times, the age of what we see is determined by how far back its journey began. So when Webb detects a galaxy from 300 million years after the Big Bang, it's not telling us that the galaxy is 300 million years old today. It's telling us the light was emitted when the universe was 300 million years old. That galaxy, if it still exists now, is nearly as old as the universe itself. 13.8 billion years, minus whatever time it took to form in the early era. But we aren't seeing that present-day version. The version we're seeing is impossibly young. A galaxy still taking shape in a universe that had only just settled down enough for stars to ignite. This makes the idea of oldest very different from how the word is used in everyday life. In astronomy, oldest is really earliest detectable. The term is an observational statement, not a chronological one. Because we can't see the universe at earlier times than the moment when light could first travel freely, the absolute floor for observation is around 380,000 years after the Big Bang, when the cosmic microwave background formed. Before that, the universe was full of free electrons that scattered light so heavily that no photon could make a straight path. Everything earlier is invisible to telescopes because the universe simply wasn't transparent yet. This is why the phrase "older than the Big Bang" collapses under basic physics. If something truly predated the universe's transparency, we couldn't see it because no light could have traveled from it. If it predated time itself, the very idea of age wouldn't even apply. So when Webb turns up an unusually bright or massive galaxy at high redshift, scientists don't think it's older than the universe. They think it formed faster or more efficiently than expected. In the same way that seeing a talented teenager doesn't mean they're older than you. It just means they developed in a way you didn't expect. The reason this distinction matters so much is that the early universe was a rapidly changing environment. The timeline between the Big Bang and the formation of the first stars was filled with processes that had to happen in sequence. First, the universe needed to cool enough for protons and electrons to combine into neutral atoms. Then, it needed gravity to gather those atoms into dense pockets. Then those pockets had to collapse under their own weight until nuclear fusion could ignite. Only then did the first stars start shining. And once the first stars appeared, their intense ultraviolet radiation began tearing electrons off atoms again, slowly re-ionizing the universe in a process that took hundreds of millions of years. It's only during the later part of this process that galaxies recognizable as galaxies begin to take shape. When Webb finds something bright in this era, scientists know it can't be older than the universe. It can only be earlier. And the reason it grabs attention is that its brightness or mass can stretch current models of how quickly the early universe built structures. Early star formation is thought to be intense but short-lived. The first stars were massive, unstable, and prone to violent ends. Their explosions seeded the cosmos with heavier elements, creating the conditions for later generations of stars to form more steadily. For a galaxy to be bright enough to stand out in Webb's data just a couple hundred million years after the Big Bang means it must have undergone a burst of star formation far stronger than most models anticipated. This is where the phrase "oldest galaxy" becomes an invitation to rethink what the early universe was capable of. Scientists don't assume the models are wrong just because a new observation pushes the limits. They look at what the new data implies about how matter behaved when the universe was young. Maybe the first stars formed in larger clusters than expected. Maybe early gas clouds collapsed more efficiently because the universe was denser. Maybe black holes formed earlier and helped accelerate the growth of early galaxies. Each of these possibilities fits comfortably within the Big Bang timeline. They simply adjust what the early phases of the universe looked like. It's also worth noting that when astronomers talk about the age of a galaxy, they're often referring to the time since its stars first began to form. But stars within a galaxy have their own individual ages. A newly observed galaxy might contain stars that are only a few million years old at the moment their light left the galaxy, even though the galaxy itself sits very early in the cosmic timeline. That's another reason the term "oldest" can feel misleading if you don't know the details. You could have a galaxy that appears at a very early cosmic time but internally contains stars at various stages of their lives. The galaxy's age refers to its place on the cosmic calendar, not the maturity of its contents. Another thing that complicates the idea of age is that galaxies evolve, merge, change shape, and grow over billions of years. The oldest galaxy ever observed today and the same galaxy observed billions of years from now would look nothing alike. We're seeing only the earliest version of it. If you were to somehow visit it in the present day, ignoring the impossibility of intergalactic travel, you would not find a tiny primitive object. You would find something that had grown, collided with neighbors, absorbed gas, birthed multiple generations of stars, and possibly housed a mature supermassive black hole. So the oldest galaxy is almost always a younger, unfinished draft of what that galaxy later became. This distinction is so central to astronomy that researchers rarely use the term oldest without specifying what they mean. They might say oldest known galaxy in terms of redshift, or earliest galaxy observed, or most distant confirmed galaxy. These phrases are all different ways of talking about the same idea. We're seeing the object as it was in the earliest stage of its life that we can detect. But because most people don't think in terms of light travel time or cosmic epochs, the simplified headline becomes oldest, and that gets quickly misinterpreted as older than everything, which is where the confusion begins. To make things even more interesting, the expansion of the universe creates a disconnect between distance and time that surprises a lot of people. A galaxy whose light took 13.4 billion years to reach us is not 13.4 billion light years away right now. Because space has been expanding during that entire journey, the current distance to that galaxy could be 30 or even 35 billion light years, depending on its redshift. So the term oldest ends up referring to when the light was emitted, not how far away the galaxy is today. The difference between emission time and present-day distance is one of the most unintuitive parts of cosmology, and it's one of the reasons astronomers talk about look-back time instead of normal distance. Look-back time tells you how long the light has been traveling. It's a direct measure of how far back in the universe's history you're seeing. What Webb does better than any previous telescope is expand that look-back time window. Hubble could see objects whose light came from maybe 400 or 500 million years after the Big Bang. Webb pushes that down to 300 million years, 250 million, and possibly even closer as observations pile up. Every time it does that, the headlines scream oldest ever, even though scientists mean earliest snapshot yet. This is part of how science moves forward. Each new observation shifts our understanding of what's possible at the dawn of the universe. But these shifts never imply that something existed before the universe itself. They imply that galaxies took shape sooner than expected, or that the early universe was more efficient at building stars than models assumed. Another layer to this is that the earliest galaxies aren't old in the sense of having long histories. They often appear clumpy, irregular, and chaotic, more like the building blocks of future galaxies than complete structures. Calling them oldest can give the wrong impression, as if they're ancient versions of the mature spiral and elliptical galaxies we see today. In reality, they're small, rapidly forming pockets of matter surrounded by vast regions of neutral gas. They're more like construction sites than finished buildings. The term oldest simply indicates that they formed during a time when the universe was still dark enough that the first stars were only beginning to light things up. The confusion also comes from the fact that the universe today contains galaxies that are almost as old as the universe itself, several of which formed shortly after the cosmic dark ages ended. If you look at those galaxies today, they are indeed incredibly old. Some are more than 13 billion years old. But when Webb looks at a galaxy at high redshift, it's not seeing the galaxy at its full age, it's seeing its baby picture. The oldest galaxy in that context is the earliest baby picture ever recorded, not the galaxy with the longest lifespan. This distinction becomes even more important when interpreting Webb's most surprising discoveries. Some of the objects it sees appear too bright, too massive, or too chemically mature for how early they appear in the timeline. These are the objects that generate headlines. But even in these cases, the word oldest isn't the right one. The correct interpretation is that these galaxies evolved faster than expected, not that they existed before the universe allowed them to. It's like hearing about a child who learned to speak unusually early. You don't assume the child is older than their birth certificate. You assume something about their development is remarkable and worth understanding. Webb's early galaxies are the cosmic equivalent of that accelerated development. The last piece of this puzzle is something astronomers call cosmic time dilation. Because the universe was smaller and denser when early galaxies formed, their internal processes happened on different timescales than processes in today's universe. A star-forming burst in an early galaxy might unfold over a much shorter period than a similar burst in the modern universe. This means early galaxies can appear to grow or brighten faster than expected if you use today's timelines as a reference. Once you account for these differences, the apparent mismatch begins to resolve. The galaxy isn't older than the universe, it's just evolving in a different environment. When you put all of this together, the phrase oldest galaxy becomes less a claim about absolute age and more a marker of how far back in time our telescopes can reach. Webb has extended that reach dramatically. It has allowed us to capture moments from the universe's childhood that were completely inaccessible before. And as those snapshots accumulate, they reshape our understanding of the early cosmos without ever challenging the fundamental timeline that begins at the Big Bang. When people talk about James Webb breaking records, they're usually referring to the galaxies it has uncovered in the first few hundred million years of cosmic history. These aren't just faint smudges in the distance. They are objects so far away that their light left them before our own Milky Way even existed as a concept. And the reason they matter isn't just that they're early, it's that many of them look far more developed, far brighter, and far more massive than the standard timeline of galaxy formation would predict. To understand why scientists are paying so much attention, it helps to look at what Webb has actually found, and how those discoveries fit into the broader picture of the universe's first era. The earliest confirmed galaxies from Webb's data come from a period roughly 280 to 350 million years after the Big Bang. That might sound like a sizable gap, but on cosmic timescales, it's incredibly close to the beginning. For perspective, if the entire history of the universe were compressed into a single year, these galaxies would appear in the first day of January. Not the first week, the first day. Everything else that has ever happened, from the birth of the Milky Way to the formation of the solar system to human civilization, would unfold in the remaining 364 days. That's how early these objects are. One of the standout discoveries is a galaxy often referred to as MOME Z14. It appears at a redshift of about 14, which means the light we're seeing left this galaxy around 280 million years after the Big Bang. Before Webb, the best we could do was redshifts around 10 or 11, corresponding to roughly 400 to 500 million years after the Big Bang. Webb didn't just nudge that record, it vaulted past it. MOAM-Z14 is interesting not only because of its distance, but because of how unexpectedly bright it is. Brightness in astronomy is tied to the number of young, massive stars in a galaxy. For this galaxy to shine so strongly that Webb can pick it out from billions of light years away, it must have formed stars at a breakneck pace. Another galaxy that grabbed headlines is JD's GS-Z14-0. Its light dates from about 290 million years after the Big Bang, and it shows a surprising amount of structure for such an early object. The galaxy isn't a featureless blob. It has regions where star formation is intense and concentrated. It looks like a galaxy that didn't waste any time getting to work. And that's where the puzzle lies. Most models predicted that galaxies this early would be small, dim, and irregular. JD's GS-Z14-0 still fits the small and irregular description, but it doesn't fit the dim part at all. It is bright enough that Webb captured it fairly cleanly, and when astronomers analysed its light, they found signs that it might be producing stars at a rate much higher than expected for the era. There's also JD's GS-Z13-0, another galaxy observed with Webb just a bit later in cosmic time. It sits around 320 million years after the Big Bang and has many of the same surprising features as the higher redshift galaxies. It is compact and full of young stars, and yet it appears to be forming those stars with remarkable efficiency. Taken one at a time, these galaxies are interesting, but not revolutionary. But as a set, they begin to paint a picture that looks different from the neat timelines astronomers had been using for decades. Part of the surprise comes from how stars were expected to form in the early universe. The first stars, often called population 3 stars, are thought to have been enormous and short-lived. They formed from pure hydrogen and helium, since heavier elements didn't exist yet. These early stars should have lived fast and died explosively, enriching the surrounding gas with heavier elements. Only after enough of these first stars lived and died could galaxies start forming more complex structures. That cycle should have taken time. Early galaxies weren't supposed to look bright and busy so soon after the Big Bang because there shouldn't have been enough heavy elements or enough gas clouds compressed tightly enough to trigger intense star-forming regions. Yet that's what Webb keeps finding. Some of the galaxies it sees look like they've already had multiple generations of star formation by the time we observe them. That doesn't mean they truly had that many generations. It just means the amount of activity happening in a short period is higher than expected. And this is the key point. Nothing about these discoveries contradicts the Big Bang. They contradict assumptions about how quickly nature worked to turn gas clouds into galaxies. Another category of Webb discoveries adds another layer to the puzzle: early galaxies with hints of surprising mass. A few candidates, still under investigation, appear to contain more stars than models predicted could form in the first few 100 million years. Even if later analysis tones down some of these early mass estimates, the trend is clear. The early universe was more efficient at forming stars and galaxies than astronomers expected. It wasn't that galaxies were older than the Big Bang, it's that galaxies might have needed less time to assemble than previously thought. There's also evidence that some of these early galaxies may host black holes far earlier than expected. Normally we think of black holes forming from the collapse of massive stars. Over time they grow by absorbing gas and merging with other black holes. For a galaxy just a couple 100 million years after the Big Bang to host a large black hole, the black hole would have needed to seed and grow extremely quickly. Webb may have spotted early signs of this in a few distant objects. If confirmed, that would force researchers to rethink the early growth stages of black holes, not because they're older than the universe, but because the universe built them faster than our standard models predicted. And one of the interesting details emerging from these discoveries is that the early universe wasn't empty or slow-moving. It was dense. Matter was closer together, so gravity had an easier time pulling gas clouds into star-forming regions. This doesn't violate anything about cosmic history. It simply means that conditions were right for faster cycles of formation. When the universe was smaller and denser, structures didn't have to wait billions of years to grow. They could assemble quickly, even explosively, if enough gas condensed in the right place. Webb's detections are giving us a clearer picture of that density-driven efficiency in action. There's also the role of dark matter to consider. Dark matter doesn't emit light, but it shapes the universe by providing gravitational scaffolding. Galaxies form within dark matter halos, regions where dark matter has clumped together enough to pull in gas. Early dark matter halos might have formed faster and merged more often than expected. This could have created the gravitational seeds for early galaxies to grow rapidly. Webb doesn't see dark matter directly, but it does see the effects. The unexpectedly mature-looking early galaxies could be signs that dark matter halos in the first few 100 million years were more active than models had predicted. Another reason these galaxies capture attention is because Webb isn't just spotting a single anomaly, it's finding a pattern. With Hubble, a galaxy like JADA's GS Z14-0 would have been invisible, or at best an ambiguous smudge that might not have been recognized as a high redshift object. But Webb has uncovered several early candidates in a relatively small portion of sky. That suggests that the early universe may have been full of galaxies like these, small, bright, and forming stars quickly. If that pattern holds, it might mean the early universe wasn't a slow start followed by rapid evolution. It might have been energetic from the beginning. Some of Webb's early galaxies also show hints of the chemistry inside them. Even at these early times, some galaxies exhibit signs of elements heavier than helium, which suggests that at least one generation of massive stars had already lived and died. This is a big clue about how quickly stellar processes were happening. For heavy elements to appear, massive stars must have gone supernova, and supernovae need time to occur. Yet Webb is seeing galaxies at 280 or 300 million years that already show signs of enrichment. This doesn't break the timeline, it simply pushes star formation earlier in that timeline than expected. Instead of galaxies taking hundreds of millions of years to go through their first cycle of star birth and star death, the cycle might have begun within the first 100 million years. The sheer brightness of some of these early galaxies also hints at something called burst mode star formation. Instead of stars forming slowly and steadily, the galaxy might experience a rapid compression of gas that triggers a burst of new stars all at once. Because young stars are hot and luminous, these bursts produce intense ultraviolet light, which shifts into the infrared by the time Webb detects it. That could explain why these galaxies appear unusually bright for their age. They aren't old, they're efficient. One of the subtler but important results from Webb's observations is that the diversity of early galaxies seems wider than anticipated. Some are compact and bright, some are diffuse and faint, and some look like they're still assembling from small clumps merging together. This diversity suggests that galaxy formation doesn't follow a single clean path. Instead, the early universe may have allowed several parallel routes for galaxies to form and grow. Some galaxies may have formed quickly in dense pockets. Others may have formed more slowly in regions with less matter. Webb is giving astronomers enough data to see this variation, whereas before, the earliest galaxies we knew about were all just faint, hard-to-interpret dots. Even more fascinating is that some of Webb's early galaxies look like they may be experiencing feedback from stars, winds, radiation, and supernovae pushing gas around. This is a process we see in modern galaxies, but the idea that it was already happening just a few 100 million years after the Big Bang shows that early star formation wasn't a gentle process. It was messy, quick, and energetic. The galaxy didn't simply accumulate gas and quietly form stars. It formed massive stars that reshaped the galaxy even as it was being born. All of this helps explain why Webb's discoveries keep grabbing attention. The telescope isn't finding galaxies that break the timeline of the universe. It's finding galaxies that break the timeline we expected for formation. The difference is important. The age of the universe is determined by multiple independent pieces of evidence: cosmic microwave background measurements, the abundance of primordial elements, the expansion rate of space, and more. A bright galaxy at high redshift doesn't contradict that framework. It just tells us that galaxies didn't wait as long as we thought to get started. Scientists aren't alarmed by that. They're excited. Because these galaxies give researchers a direct window into the moment when the universe was transitioning from darkness into light, a period known as the cosmic dawn. Before Webb, most of what we knew about that era came from simulations and educated guesses. Now we're getting first-person evidence directly from the light emitted in those early epochs. It's like going from reading summaries of ancient history to suddenly finding a library full of original documents. Webb's early galaxy discoveries aren't rewriting the age of the universe. They're rewriting the story of how quickly the earliest structures emerged. And each new discovery adds another piece to that puzzle, showing that the first galaxies may have been surprisingly ambitious architects, building themselves rapidly in a universe that was still settling into its new existence. Anytime a telescope uncovers something unexpected, especially something from the universe's earliest moments, it's easy for the conversation to drift toward big, dramatic claims. You'll hear people ask whether Webb has found galaxies older than the Big Bang, or whether the entire timeline of cosmic history needs to be thrown out. The truth is simpler and more interesting. These discoveries don't threaten the Big Bang at all. They sharpen it, they fill in gaps, they replace assumptions with direct evidence. But they don't overturn the fundamental framework that describes how the universe expanded from an extremely hot, dense state into what we see today. The reason these findings don't break the Big Bang starts with what the Big Bang actually says. It doesn't claim the universe exploded from a point into existing space. It describes space itself expanding from an earlier state that was far denser and hotter than anything that exists now. That expansion timeline is built on several independent observations. Webb's discoveries need to challenge all of them simultaneously to cause real trouble, and they don't. Let's walk through why. One important anchor is the cosmic microwave background, the faint glow left over from when the universe was about 380,000 years old. This radiation has been measured with extreme precision. It's not a rough estimate, it's a map of the universe's early density patterns, down to tiny variations. That map lines up with a universe about 13.8 billion years old. To break the Big Bang, the early galaxies Webb sees would have to demand an entirely different age from that map, something wildly out of sync. They don't. The galaxies Webb detects sit comfortably within the timeline set by the microwave background. Their distances match the expansion rate we measure. Their redshifts match the stretching of space. They don't appear before the Big Bang, they appear right after it, exactly where they should. Another anchor is the abundance of the lightest elements: hydrogen, helium, and trace amounts of lithium. Those elements were forged in the first few minutes after the Big Bang. Their proportions today match what nuclear physics predicts would arise from a young, rapidly expanding universe. Webb's early galaxies don't change those proportions. They don't suggest those elements were created earlier or in a different way. The chemistry of the early galaxies Webb sees still shows the signature of that primordial mixture. If the galaxies were somehow older than the Big Bang, their chemical fingerprints would look completely wrong. The redshift measurements themselves are another check. A redshift of 14 doesn't mean older than the Big Bang. It means the light left its source when the universe had expanded just enough that wavelengths stretched into the infrared by the time they reached us. Redshift is tied directly to the expansion of space. You can't get a redshift larger than what the age of the universe allows. Webb isn't spotting redshifts of 20, 30, or 200. It's spotting redshifts consistent with a universe that had already begun expanding but was still extremely young. The galaxies Webb sees are very early, but they aren't out of bounds. Every one of them fits into the same expansion curve used for decades. So if nothing about the Big Bang is being challenged, what is being challenged? Mostly the details of galaxy formation. For years, astronomers assumed early galaxies would grow slowly. They expected the first structures to be small, dim, and chaotic, taking hundreds of millions of years to build enough stars to shine brightly. Webb showed that some galaxies formed stars much faster than that. The universe wasn't quiet in its early years, it was efficient. Dense pockets of dark matter helped gas collapse faster. Early stars were massive and short-lived, pumping out enough radiation to push later generations of stars to form rapidly. These mechanisms were always possible within the Big Bang framework, they just weren't fully included in earlier models. There's also a psychological factor worth mentioning. For a long time, the earliest universe was out of reach. When you can't see something, you fill gaps with the simplest possible assumptions. Now, Webb is giving us direct data from those early eras, and the picture is messier, louder, and more energetic than the neat diagrams in old textbooks. That's not a problem. That's progress. Some of the misunderstanding comes from how surprising brightness gets interpreted. When Webb finds a galaxy that's brighter than expected, it doesn't mean the galaxy is older. Brightness is not an age indicator. It's a sign of rapid star formation. A galaxy can be extremely young and still extremely bright if it's forming stars at an intense rate, especially massive stars. These massive stars burn hot, die quickly, and dramatically influence their environment. Put enough of them in a small space and the galaxy will shine far beyond what older, quieter galaxies produce. Webb is showing that early galaxies didn't wait long to start that process. Another piece of the confusion revolves around the idea of mature structures. Some of Webb's early galaxies look structured enough that they might resemble later galaxies. But structure doesn't prove age, it proves activity. When matter is dense and star formation is rapid, galaxies can develop clumps, bursts, and internal variation quickly. These aren't fully settled galaxies like the Milky Way. They're more like cosmic construction zones, busy, bright, and fast-moving. Calling them too mature is a misunderstanding. Their apparent maturity is the result of a fast pace, not a long timeline. And then there's the claim that dark matter halos might have formed faster than expected. If true, that would help explain why galaxies assembled so quickly. But again, this doesn't push anything before the Big Bang. It simply changes how gravitational collapse behaved in the universe's early ages. Dark matter is one of the main architects of structure, and if its early behavior was slightly different from what simulations predicted, that's a detail to adjust, not a crisis. Another important point is that Webb's earliest candidates still go through rigorous confirmation. A galaxy initially labelled extremely old based on photometry might later be revealed to be closer and dustier, which would change the interpretation. This has already happened with a few early candidates. Webb's spectrometers have gotten very good at settling these questions, which is one reason why the current confirmed highest redshift galaxies are trustworthy within the timeline. So while headlines often jump ahead, the scientific process remains careful. The most useful way to think about all of this is simple. The Big Bang describes the beginning of expansion, not the pace of what came after. The expansion sets the stage, but the universe decides how quickly it wants to build galaxies based on its conditions, and early conditions favored speed. Dense matter, strong gravity wells, massive stars, and frequent mergers all contribute to rapid galaxy growth. Webb's discoveries reinforce that picture rather than contradicting it. The bottom line is that the universe didn't form galaxies later than expected. It formed them earlier than expected. That's not evidence against the Big Bang. It's evidence that the universe was incredibly efficient right out of the gate. Webb is showing us that when conditions were right, stars and galaxies didn't creep into existence. They surged into existence. The timeline stays intact. The physics stays intact. The story just gets more dynamic. When people hear that Webb is spotting galaxies only a couple 100 million years after the Big Bang, the reaction is usually the same. How could anything form that fast? It feels like there's a mismatch between how enormous galaxies are and how little time they had to assemble. And that's where many of the misconceptions come from. The discoveries are surprising, yes, but they aren't impossible. They're only unexpected because older models filled the early universe with slow, gentle growth. Webb is now revealing that the first era of cosmic structure wasn't slow or gentle at all. It was intense, crowded, and fast-moving, and those conditions are exactly what you would need to build galaxies quickly. The first thing to understand is that the early universe wasn't a quiet, empty space waiting for stars to appear. It was dense, incredibly dense. If you could somehow travel back to the first few 100 million years, you'd be in a universe where matter was packed together far more tightly than today. Gravity works faster when things are closer. Clouds of gas can collapse more quickly. Small clumps merge more often. And the universe at that time was full of these clumps, all tugging on each other and collapsing into the first structures. So when Webb spots a galaxy at 280 or 300 million years, the shock value isn't that the galaxy is too old. It's that we underestimated how efficiently that early density helped things form. Dark matter is a major part of that efficiency. It doesn't emit light, but it makes up most of the mass that shaped the early universe. Right after the Big Bang, dark matter started clumping into halos. Imagine invisible wells of gravity that ordinary gas falls into. These halos formed fast. Some merged, some grew, and inside them, gas began collapsing to form the first stars. Webb's discoveries strongly hint that these halos were forming earlier and with more variation than simulations predicted. That isn't a contradiction, it's an upgrade. If halos were ready earlier, then galaxies had places to form earlier. Then there's the nature of the earlier stars themselves. They weren't like the Sun. They were enormous, sometimes hundreds of times its mass. With only hydrogen and helium to work with, these stars couldn't cool efficiently, so they grew large before igniting. Large stars burn fast and bright. They pump out intense ultraviolet light. They explode sooner. This kind of behavior helps galaxies grow quickly. Each massive star explosion stirs the surrounding gas, compressing pockets that can trigger new waves of star formation. The earliest galaxies weren't quietly glowing objects. They were more like cosmic fireworks factories, with one generation of stars triggering the next in a rapid cycle. Webb's observations fit neatly into that picture. A small, dense galaxy full of massive stars would appear extremely bright in the ultraviolet, light that is now shifted into the infrared by the universe's expansion. So when we see a bright early galaxy with Webb, it doesn't mean it's old. It means it's intense. A short-lived starburst can make a galaxy shine dramatically, even if it's barely formed. That brightness is what makes these galaxies stand out in the first place. The next piece is mergers. Galaxies didn't grow from smooth, isolated clouds. They grew from small clumps, smashing together repeatedly. Each merger adds mass, stirs gas, and triggers more star formation. The early universe didn't have much volume, so these clumps ran into each other frequently. That's one reason some of Webb's galaxies look surprisingly active. They may be mid-merger or just past one. A single merger event can transform a faint, quiet object into a bright, chaotic one in a very short time. That means brightness doesn't equal age. It often equals recent activity. Another factor is that models before Webb were limited by the telescopes available. When Hubble pushed into the farthest distances it could reach, it revealed galaxies that were tiny and faint because only the brightest ones crossed its detection threshold. Webb goes deeper and sees more diversity: bright, faint, structured, chaotic. That makes it clear that the early universe wasn't dominated only by low-mass objects. It had a mix, and Webb is simply capturing the brightest tip of that mix first. The surprises come from the fact that we finally have the sensitivity to see them. Even the measurements that estimate mass for these early galaxies are more uncertain than most people realize. A galaxy's brightness tells you how many stars are shining right now, but it doesn't tell you the total number of stars already formed unless you know their types, ages, and distribution. In the early universe where massive stars dominate, a small number of large, bright stars can mimic the light of a much bigger population. That means some early estimates tend to inflate the apparent mass. As better spectroscopy comes in, many too massive galaxies get revised downward, not because the universe was slower, but because our early guesses have become more precise. We also have to account for how much dust existed in these galaxies. In modern galaxies, dust dims and reddens starlight. In early galaxies, dust was scarce because it takes multiple generations of supernovae to produce it. With less dust, more of a galaxy's light escapes directly into space. In other words, an early galaxy with the same number of stars as a modern galaxy can appear significantly brighter. Webb sees the unfiltered output of these early starbursts, making them look more luminous than galaxies of similar size in today's universe. Some people also wonder how black holes could appear so early. Webb has detected hints that black holes, larger than expected, may exist in some early galaxies. But this doesn't break anything. There are several viable pathways for early black hole growth: the collapse of giant primordial gas clouds directly into black holes, the merging of smaller early black holes, or rapid accretion from dense gas-filled environments. All of these become more efficient in a dense young universe. That means early black holes may grow quickly without violating the timeline or requiring exotic physics. Another point to consider is how the rate of star formation changes over time. Early on, the universe could funnel gas into tiny halos at incredible speed. Later, as space expanded and matter thinned out, the rate slowed, so it's not surprising that early galaxies grew faster. Modern galaxies like the Milky Way couldn't recreate that pace even if they tried. The early universe simply had different rules because it had different conditions. Finally, one of the clearest signs that nothing here breaks cosmology is this: the galaxies that Webb sees at these record-setting distances still get dimmer and rarer as we approach earlier and earlier redshifts. If galaxies truly existed before the Big Bang, or before the expected timeline, we'd see a sudden population of objects at impossible redshifts. We don't. Observations follow the smooth decline predicted by the expansion of space. Everything lines up, so when a headline says, "Webb found something older than the Big Bang," it's misunderstanding the story. Webb is showing us that the first few 100 million years weren't a slow crawl. They were a rapid build-up driven by density, dark matter scaffolding, massive early stars, and frequent mergers. The universe wasn't waiting around, it was busy from the start, and now we finally have the tool sensitive enough to witness that rush of activity. So redshift is one of those ideas that gets mentioned constantly, yet it's easy for it to feel abstract. And when people hear that Webb is spotting galaxies with redshifts of 12, 13, 14, and beyond, it's natural to wonder what those numbers truly mean. Redshift is central to interpreting Webb's discoveries because it tells us when the light was emitted, not just how far the object is. Once you understand redshift cleanly, the whole older than the Big Bang confusion disappears. So let's break it down in a straightforward way, without jargon and without assuming you're already an astrophysicist. Redshift is simply what happens to light when the space it's traveling through stretches. As the universe expands, every photon stretches with it. Short wavelengths become longer. Blue shifts toward red. Red shifts toward infrared. Infrared can stretch into even longer wavelengths. That stretching doesn't happen because the light slows down. It doesn't. The speed of light stays the same. The wavelength changes because the space between wave peaks has expanded. Now, the key point, redshift is a measure of how much that stretching has happened. If a galaxy has a redshift of 1, that means its light has doubled in wavelength. A redshift of 10 means it has been stretched 11-fold. A redshift of 14 means the light Webb sees is 15 times longer than it was when it left the galaxy. When Webb detects extremely high redshifts, it's seeing evidence that the universe was tiny compared to what it is now. This is where misunderstandings often start. Redshift isn't age directly. It's not as simple as a redshift of 10 means 10 billion years old. Instead, each redshift corresponds to a moment in the universe's expansion history. The math behind that mapping depends on how fast the universe was expanding at different times. When astronomers say a galaxy is from 280 million years after the Big Bang, that comes from mapping its redshift onto the expansion timeline measured by other tools, the cosmic microwave background, supernova distances, and the values of cosmological constants. When all those things line up, we get a consistent picture. So a galaxy at redshift 14 isn't older than the universe. It's exactly where it should be if the universe is 13.8 billion years old. It's simply from a moment very close to the beginning, about 2% of the universe's entire age. This is why redshift is so powerful. It lets us see not just where something is, but when it emitted the light we're now capturing. The next piece of the puzzle is how redshift is measured. There are two main methods, photometric and spectroscopic. Photometric redshift is basically an educated estimate. You look at how bright an object is through different filters, each filter catching a specific range of wavelengths. Because neutral hydrogen in the early universe absorbs ultraviolet light, early galaxies have a sharp drop in brightness at a specific wavelength called the Lyman break. As the universe expands, that break shifts into the infrared. Webb is designed to catch that shift. When the drop lands in a certain filter, you can estimate the galaxy's redshift. But estimates can be fooled. A dusty galaxy much closer to us can sometimes mimic the same pattern. That's where spectroscopic redshift comes in. Spectroscopy actually stretches out the light into a precise spectrum and measures the movement of known lines. Hydrogen emission, oxygen lines, etc. That shift tells you exactly how much the light has been stretched. This method is far more accurate. When you hear that a galaxy is confirmed at a certain redshift, that confirmation almost always comes from spectroscopy, not photometry. Webb's spectrometers are the reason early candidates that once looked questionable are now being pinned down with confidence. Another important thing to understand is that redshift is not limited by the speed of light in the same way traditional distance is. Some galaxies are receding from us faster than light, not because they're moving through space that fast, but because space itself is expanding. That's allowed in general relativity. It's one more reason redshift is the right tool for the job. You can't use ordinary distance measurements for objects this far away because the idea of distance becomes fuzzy when space is stretching. Redshift bypasses that problem by directly measuring the stretching. When Webb picks up a galaxy at redshift 13, that means the universe was roughly 3% of its current size when the light left. If Webb picks up something at redshift 15, that means even closer to the beginning. But here's the crucial part. Even if Webb spots something at redshift 20 someday, that would still be after the Big Bang. It would simply be showing us the first 150 million years instead of the first 300. The Big Bang isn't being squeezed or redefined by these numbers, we're just filling in earlier chapters of the same story. Redshift also helps explain why early galaxies look tiny and faint in Webb's images. The universe's expansion doesn't just stretch light, it increases the distance the light must travel, and it dilutes the brightness. A galaxy that was once compact and vigorous might arrive to us as only a handful of pixels, but within those pixels are photons that left their source when the universe was only a few 100 million years old. The light isn't old in the sense of being older than the universe. It's old in the sense of having been traveling almost the entire age of the universe to reach us. Now, the reason high redshift discoveries draw so much attention is that they probe the cosmic dark ages, the time between the Big Bang and when the first stars and galaxies lit up the universe. Before stars existed, the cosmos was filled with neutral hydrogen that absorbed most ultraviolet light. As the first stars formed, they ionized the surrounding gas, creating pockets of transparency. The redshift at which this transparency spread across the universe is somewhere around 6 to 10. That means galaxies at redshift 12, 13, or 14 are sitting right inside this transition zone, the era where the universe is switching from darkness to structure. Seeing galaxies this early tells us something important. Star formation must have begun earlier than these observed redshifts. If we're looking at galaxies that are already up and running at 280 million years, that means stars must have been forming well before that. This is exactly why scientists get excited. The earlier we push confirmed redshifts, the earlier we push the beginning of structure formation. But none of that implies galaxies existed before the Big Bang. Redshift doesn't allow it. The expansion timeline doesn't allow it. The cosmic microwave background doesn't allow it. These galaxies aren't challenging the timeline, they're helping pin down the moment structure began to appear within it. Redshift even helps explain why surprisingly bright galaxies at high redshift don't break cosmology. Because the universe was smaller then, galaxies were physically closer to each other. Gas fell into dark matter halos quickly. Massive stars ignited quickly. Brightness at early times doesn't require age, it requires intensity, and the conditions were perfect for intensity. There's also an observational effect called surface brightness dimming. As redshift increases, galaxies appear dimmer, not just because of distance or stretching, but because their light is spread out over a larger area when it reaches us. Webb's infrared sensitivity helps compensate for this effect. That's why Webb, and not Hubble, is finding galaxies at these extreme distances. It's not because they didn't exist before the telescope was launched, it's because we finally have the instrument sensitive enough to detect them despite enormous dimming. There's a final important point: the redshift values. Webb measures line up perfectly with the expansion pattern predicted by standard cosmology. If the Big Bang framework were breaking down, we'd expect redshift distance relationships to bend or drift in ways that don't match the models. Instead, the opposite is happening. The more Webb sees, the more tightly everything fits. The early universe might be busier than we predicted, but its expansion history remains consistent. So when Webb reveals a galaxy at redshift 14, it's not spotting something that shouldn't exist. It's showing us something we've never been able to see before. Light stretched by billions of years of expansion, carrying the story of a universe that was already building itself at a furious pace. Redshift is the key to translating that story, and the translation lines up perfectly with the Big Bang. When Webb released its very first deep field images in mid-2022, something unusual happened. Within days, social media, blogs, podcasts, and even a few news outlets started making claims that Webb had discovered galaxies that shouldn't exist. Galaxies that were older than the Big Bang, or galaxies that broke cosmology. A few scientists even gave interviews suggesting the data might force a rewrite of the standard model of cosmology. Those comments got amplified, repeated, and pulled out of context until they grew into something far bigger than the evidence ever supported. To understand why those headlines spread so fast, and why they turned out to be wrong, you have to look at the mix of early data, natural scientific uncertainty, fast-moving interpretations, and the way attention works online. The story starts with how early Webb data was released. Astronomers around the world were eager to test the telescope's capabilities, and as soon as the first images became available, teams began analyzing them at breakneck speed. The problem is that scientific rigor takes time. Confirming a galaxy's distance requires careful spectroscopy. But estimating a galaxy's distance, using only brightness and color, is much faster, even though it's also far less reliable. Those early photometric redshifts produced a rush of candidates that appeared to be extremely distant, maybe even farther than anything Hubble had ever spotted. Many of these early candidates were labeled potential record breakers, and that's where the misunderstanding began. The word candidate didn't always make it into the headlines, neither did the phrase photometric estimate. Instead, the public saw sweeping statements like Webb finds a galaxy only 250 million years after the Big Bang, even though the actual scientific papers were far more cautious. That gap between careful science and viral excitement created the perfect storm. If even one estimate pushed the numbers a little too far, you ended up with claims that the galaxy was impossibly bright or impossibly massive for its age, and once those claims were out there, they spread faster than any correction ever could. To be fair, some of the early photometric candidates were surprising. A few looked bright, brighter than expected for the first few 100 million years. A few looked compact but structured, which some people took to mean mature. And because the data was fresh, many teams were publishing rapid analyses that hadn't yet gone through the slower, more careful peer review process. What the public often saw were the most eye-catching interpretations from the quickest papers, not the settled picture that emerged months later. One of the earliest sparks for the impossible galaxy narrative came from a handful of preprints that claimed certain galaxies appeared far too massive for their era. The analysis suggested that these galaxies contained as many stars as medium-sized modern galaxies, even though they existed 300 million years after the Big Bang. But those mass estimates were based on several assumptions that didn't hold up under scrutiny. They assumed the galaxy's light was coming from a typical mix of stars like those in the present-day universe. They assumed the galaxies weren't dominated by massive, short-lived stars that inflate brightness without adding long-lasting mass. And they assumed dust didn't play a role in shaping the observed colors. Once those assumptions were tested, the mass estimates dropped significantly. These galaxies weren't monsters breaking the timelines. They were intensely star-forming objects whose light was dominated by massive stars. In other words, they were bright, not bulky. But by the time that clarification came out, the initial sensational headlines had already taken off. There was another factor behind the confusion. A few scientists made bold statements in interviews before the data was fully confirmed. In science, it's normal to discuss surprising preliminary results. It's part of the process. But quoted without context, those early comments sounded like declarations that cosmology had collapsed overnight. One astrophysicist remarked that the galaxies looked too evolved too soon, a phrase that spread across dozens of headlines. The word evolved was interpreted to mean old, when the intended meaning was active. A galaxy can be evolving quickly without being old at all. But nuance rarely survives the journey from a research preprint to a viral headline. Another critical detail behind the early claims was the confusion between apparent maturity and actual maturity. When astronomers say a galaxy looks mature, they don't necessarily mean it has had billions of years to grow. They mean it shows signs of organized star formation, structured gas regions, or internal variation. Those features don't require age, they require intensity and density. In the early universe, with everything packed close together, it doesn't take long for gas to collapse into clumps or for stars to trigger new waves of starbirth. A galaxy can look mature after only a few tens of millions of years if the environment is intense enough, but that subtlety didn't make it into most headlines. Part of the confusion also came from how striking Webb's images are. Early deep fields showed dozens of tiny, bright objects sprinkled across the background. Many of these were candidate galaxies from the first few 100 million years. To a trained astronomer, this was exciting but expected. Webb was designed to detect exactly those objects. To someone less familiar with redshift scaling and observational limits, it looked like the universe was full of ancient galaxies that shouldn't exist yet. The misconception grew when people assumed brightness equals age, which isn't true. Brightness can just as easily indicate intense star formation or the presence of very massive stars, both of which were far more common early on. Another early complication was the existence of interlopers. These are galaxies or objects that look like high redshift galaxies but turn out to be much closer. A dusty galaxy at moderate redshift can sometimes mimic the colors of a very high redshift galaxy. especially if only photometric data is available. Some of the most extreme early candidates turned out to be exactly that, interlopers. Once spectroscopy came in, their redshifts were revised downward by billions of years. But again, by the time the corrections arrived, the drama had already circulated. There's also a human factor behind the viral spread. People love big, sweeping statements. Webb confirms early galaxy formation is faster than expected, doesn't travel nearly as far as Webb breaks the Big Bang. And once a dramatic claim is out there, even if it's based on a misunderstanding, it becomes part of public conversation. Videos get made, posts get shared, memes pop up. The correction always arrives, but it doesn't get the same traction because it doesn't have the shock value. Even within scientific communities, Webb's early results prompted a healthy amount of recalibration. Models of early galaxy growth had been built on incomplete data since telescopes before Webb simply couldn't see faint infrared objects at extreme distances. The first few months of Webb observations showed that galaxies formed faster and started shining sooner than simulations suggested. That led to revisions of star formation efficiency, halo formation, and early stellar populations. But these revisions stayed within the framework of modern cosmology. It wasn't a rewrite of the universe's origin, it was a refinement of the early timeline. Another ingredient behind the confusion is that terms like too massive, too bright, or too early aren't absolute. They're relative to predictions. And predictions are only as good as the assumptions behind them. Before Webb, predictions were based on limited visibility into the early universe. Now that Webb can see deeper, the predictions need updating. That's not a crisis, it's how science always evolves. Models get better when new data arrives. Something similar happened when Hubble was launched. Early images showed galaxies that looked smaller, stranger, and more varied than expected. That didn't break cosmology, it enriched it. Webb is simply doing the same thing at earlier times. The irony is that in many ways, Webb's early discoveries actually validated the foundation of modern cosmology. Redshift values followed the expected expansion curve. The distribution of objects matched predictions. None of the galaxies existed before the cosmic microwave background formed. No object appeared at a redshift that violated the age of the universe. Everything lined up, just with more activity and earlier star formation than anticipated. If anything did change after those early headlines, it was the public's appreciation for how dynamic the first few 100 million years were. The universe wasted no time assembling structure. Gravity acted quickly in a dense environment. Dark matter halos seeded early formation. Massive stars ignited rapidly. Starbursts lit up galaxies in short, spectacular episodes. All of this fits within the Big Bang framework. None of it contradicts the expansion history. The universe wasn't older than we thought, it was simply busier. So why did some people continue insisting that Webb had disproven the Big Bang? Because once a dramatic idea catches on, it sticks. It becomes a narrative, and narratives are harder to correct than data. But the actual science, the spectroscopy, the redshift confirmations, the modeling updates, never pointed to anything breaking the timeline of the universe. What Webb truly showed is that the first stars and galaxies formed earlier and grew faster than older telescopes could detect. That's not a contradiction. That's a discovery, and it's a reminder that the more clearly we can see the universe, the more intricate its story becomes. Not older, not contradictory, just richer and more detailed than we ever expected. One of the most important questions behind all the early universe confusion is much simpler than the headlines made it sound. It isn't, did something exist before the Big Bang? Or is the Big Bang wrong? The real question scientists debated was this: how fast could the first stars realistically form once the universe began? Webb didn't undermine cosmology. It sharpened a debate that had already been simmering for years, even before the telescope launched. To understand the debate, you have to picture what the universe looked like right after the Big Bang. For the first few tens of thousands of years, the universe was a hot, dense plasma where light couldn't travel freely. As it expanded and cooled, protons and electrons finally combined to form neutral hydrogen. That moment left behind the cosmic microwave background. After that, the universe entered a long, dark period where there were no stars, no galaxies, just diffuse cooling gas and the invisible scaffolding of dark matter halos forming under gravity. The first question in the debate was, how quickly could that gas fall into dark matter halos and get dense enough to ignite the very first stars? Before Webb, most models suggested that this started maybe 200 to 300 million years after the Big Bang. But those were broad estimates, not hard limits. They were based on simulations that couldn't fully account for the detailed physics of cooling gas, turbulence, and how early dark matter halos grew. Another part of the debate focused on how efficient early star formation could be. Efficiency means, out of all the gas inside a young halo, how much actually ends up in stars. In the modern universe, the efficiency isn't very high. Galaxies have magnetic fields, supernova explosions, black hole activity, and turbulence, all of which make star formation messy and slow. But in the early universe, the situation was different. There were no previous generations of stars to stir things up, no complex magnetic structures, no heavy elements to alter cooling, just simple hydrogen and helium, ready to collapse under gravity. So the big argument went like this. Some researchers believed early star formation must have been slow because the gas was warm and took time to cool. Others argued that because the early universe was extremely dense and dark matter halos formed faster, star formation could have been extremely rapid, much faster than present-day galaxies. Webb's observations gave the second group a major boost. When it found galaxies shining brightly only 300 or so million years after the Big Bang, that implied stars were forming quickly, and in significant numbers. But that doesn't require exotic physics. It just means the early universe was more efficient than predicted in turning gas into stars. One thing that made early star formation potentially faster was the fact that the first stars, known as population 3 stars, were thought to be enormous. With no heavy elements, gas clouds couldn't cool as effectively, which favored the formation of massive stars, sometimes hundreds of times the mass of the Sun. These stars burned extremely hot and extremely bright for only a short time before exploding as supernova. Those explosions seeded the next wave of star formation with heavier elements, which cooled the gas more effectively and made the next generations of stars smaller and more numerous. This cycle of rapid formation, ignition, and explosion could repeat quickly in the early universe. A few bursts of this activity could build a surprisingly bright young galaxy in a very short time. So when Webb sees a compact but bright galaxy at high redshift, it's not seeing something old, it's seeing something intense. Part of what fueled early confusion is that we don't actually have direct observations of population 3 stars yet. They're too faint and too short-lived to catch individually, and their signatures get blended into the larger glow of the galaxies they inhabit. Because we've never observed them head-on, all of our predictions about how they behave are based on simulations. So when Webb showed galaxies forming faster than expected, some people jumped to the idea that the simulations must be wrong in a fundamental way. But simulations aren't the laws of physics, they're approximations. Webb's data simply told us the simulations needed better assumptions about cooling rates, gas collapse, and early halo behavior. Another element of the debate involved feedback, specifically how early stars affected their surroundings. In modern galaxies, star formation can be slowed down by the stars themselves. Radiation from young stars heats surrounding gas. Supernovae blast gas out of galaxies. Black holes inject energy into interstellar space. All of these things regulate star formation and prevent a galaxy from turning all its gas into stars at once. But in the very first galaxies, before dust and metals existed to trap energy, the balance between feedback and collapse might have worked differently. Feedback could have been weaker, giving gravity a wider window to act before the first stars pushed back. That would allow early galaxies to build up bright, dense cores quickly, exactly the kind of objects Webb is now detecting. Another piece of the puzzle relates to the size of early dark matter halos. The distribution of dark matter determines where galaxies can form. Before Webb, some models assumed that the earliest halos capable of forming stars would be relatively small. But Webb's early data hinted that small halos may have merged rapidly into larger ones. Bigger halos can hold more gas and form stars faster. The surprise wasn't that galaxies existed early, it was that their halos may have assembled much faster than earlier simulations guessed. A few researchers proposed more dramatic explanations in the early days, like exotic dark matter that interacts differently or hypothetical new forces that could speed up early collapse. But as more Webb data came in, these extreme explanations lost traction. There was no need for new physics. A combination of faster halo growth, efficient gas cooling in dense environments, and massive early stars can explain the brightness of young galaxies without breaking any part of cosmology. The last component in the debate was observational bias. This is something that often gets overlooked outside scientific circles. Webb is incredibly good at spotting the brightest galaxies, not the average ones. When people looked at the first Webb data, they saw bright galaxies at high redshift and assumed these were representative. But bright galaxies are outliers, rare objects that stand out because they're easier to detect. The average galaxies at that time were likely much dimmer, smaller, and harder to see. As Webb spends more observing time on deep fields, we're starting to build a fuller picture, and it looks much more reasonable than the initial spike suggested. So once the dust settled, the scientific debate resolved into a clearer view. The early universe formed stars and galaxies more rapidly than expected, but still within physical limits. The physics didn't break. The Big Bang didn't wobble. The early models just needed better data to refine their assumptions. Webb provided that data, and with it, we now have a more accurate picture of how quickly the cosmos switched on its first lights. The real result of all this isn't that something is older than the Big Bang. It's that the Big Bang led to a universe that hit the ground running far sooner than we thought. Gravity wasted no time building the first structures, and the first stars burned fiercely enough to light up galaxies in a cosmic instant. A big part of the confusion around Webb's earliest results came from how we talk about mature galaxies. That word slipped into public discussions again and again, and every time it did, people understandably jumped to the same conclusion. If a galaxy looks mature, it must have lived long enough to become mature. But in cosmology, mature doesn't work like the way we talk about people or plants or civilizations. With galaxies, especially early ones, appearance is not age, and Webb is the perfect example of why. If you looked at Webb's early high redshift candidates in mid-2022, some of them did look surprisingly organized. They weren't huge spirals with sweeping arms, but they also weren't just shapeless gas clouds. A few had bright cores, some had faint hints of rotation, and some appeared compact, almost like small versions of modern dwarf galaxies. To many observers, especially those outside cosmology, that visual impression felt like a contradiction. How could something that early be structured? How could something so young look like it had already been through millions of years of development? The answer is that galaxies don't need old age to show structure. They just need density, gravity, and intense star formation, all of which were abundant in the early universe. When gas clouds collapse in a crowded environment, they clump, ignite, and sculpt themselves quickly. Structure is a byproduct of activity, not a sign of time. A lot of the misunderstanding comes from thinking about galaxy evolution using modern examples. In the contemporary universe, forming a galaxy that has defined features, like a bright central region, rotating gas, or active star-forming clumps, can take hundreds of millions of years. But that's because galaxies today evolve slowly. They're spread out, gas is less available, and star formation is heavily regulated by feedback, black holes, and turbulence. Everything takes time because everything is operating in a sparse, calm environment. But the early universe was the opposite of calm. At redshift 12 or 13, space was dense, temperatures were different, and halos were merging frequently. Stars ignited in tight clusters, gas fell into gravitational wells rapidly, mergers happened constantly, radiation was intense. Nothing about that epoch resembled the slow, steady evolution we see today. That difference matters because maturity indicators in early galaxies aren't tied to age, they're tied to conditions. A small, dense region of gas can collapse into a bright star-forming node in just a few million years. When several of those nodes form close together, you get a compact galaxy with what looks like internal structure. It may look settled, but it's only because the processes shaping it operate on fast timescales under extreme conditions. Another way to think about this is to imagine a forest. In a well-established modern ecosystem, it might take decades for a mature tree canopy to form. But in a fast-growing environment with rich soil, constant rainfall, and intense sunlight, you can get a recognizable canopy in a fraction of the time. The final product looks similar, but the timeline and mechanisms are totally different. The same logic applies to early galaxies. One of the biggest reasons Webb's early galaxies appeared mature was their brightness. But brightness isn't an age signal, it's a star formation signal. A galaxy full of massive, short-lived stars will shine fiercely for a brief period, even if it's only a few tens of millions of years old. Those stars burn through their fuel rapidly and explode, leaving behind the next generation. When Webb sees an early galaxy glowing intensely, it's detecting fierce activity, not accumulated history. Another factor is compactness. Many of the earliest galaxies Webb detects are extremely small, often only a few hundred parsecs across. That's tiny compared to modern galaxies. But small galaxies grow bright quickly because their dense cores bunch star formation into tight regions. That concentration creates a visual impression of maturity even when the actual age is short. A small choir singing loudly can fill a room as effectively as a huge orchestra. Volume isn't always a measurement of size or longevity. A common misconception is that if a galaxy has a well-defined shape or a bright central region, it must be old. But simulations show the opposite. In the early universe, gas falls into halos along filamentary streams that guide material directly to the center. That flow can create bright cores before the galaxy even has time to develop full rotational support. In modern galaxies, bright cores often mean age. In ancient galaxies, bright cores often mean inflow. A related misunderstanding involved the presence of heavy elements. Some early Webb spectra showed signs of oxygen or other elements in galaxies around 300 million years after the Big Bang. To some observers, this looked like evidence of old age. After all, heavy elements take generations of stars to build. But those generations don't need billions of years. One cycle of massive stars can seed a galaxy with detectable oxygen in just a few million years. Massive stars burn violently, explode quickly, and enrich their environment almost immediately. A few bursts of this process give a galaxy a chemical signature that looked mature to early observers, even though the timeline required is short. Webb's infrared sensitivity also played a role in the confusion. The telescope is picking up light that Hubble never could, especially the glow from heated dust and gas. Dust in particular forms quickly around supernova explosions. A young galaxy with a handful of early massive stars can produce dust surprisingly early. In Webb's eyes, dust can make a galaxy look smoother, warmer, or more settled than it actually is. It gives an illusion of age simply because we're seeing wavelengths that older telescopes missed entirely. Another point that fueled misunderstandings was the variety among early galaxies. Webb revealed that even a few hundred million years after the Big Bang, galaxies weren't all identical. Some were tiny and chaotic. Some were compact and bright. Some seemed irregular. Some seemed surprisingly calm. That diversity led people to assume the calm-looking ones must be older. But diversity doesn't imply age. It implies that galaxy formation is messy and depends on local conditions: merger history, gas supply, halo mass, and environment. It's a bit like watching a time-lapse of a crowded city forming. Some neighborhoods boom quickly, some sprawl slowly, some rise vertically, some stay low and dense. Early galaxies are like that city, patchy, varied, and shaped by their context, not by a single clock. Perhaps the clearest example of this misunderstanding came from claims about disk-like galaxies in the early universe. A few Webb images hinted at structures that looked flattened or elongated, prompting speculation that early galaxies had developed disks much earlier than expected. But follow-up work showed that many of these shapes were illusions caused by gravitational lensing, or the way faint pixels get stretched in deep images. Some objects weren't disks at all, they were clumps seen through distorted arcs. Others were simply compact galaxies viewed at angles that made them appear elongated. Even in cases where a few early galaxies did show hints of rotation, that doesn't imply they'd been around for hundreds of millions of years. Rotation can begin early if the inflow of gas happens in a stable, coherent direction. A young galaxy doesn't need a long history to begin spinning. It needs a persistent flow of gas feeding it. That flow acts like a torque, giving it angular momentum. Rotation isn't proof of maturity, it's proof of organized feeding. One of the reasons astronomers emphasize this point is to avoid the trap of using modern galaxy categories to interpret ancient galaxies. Terms like spiral, elliptical, dwarf, or irregular don't map cleanly onto early epochs. The first galaxies weren't smaller versions of today's galaxies. They were different kinds of objects entirely, shaped by a universe still settling from its explosive beginning. Webb is also detecting many galaxies near the so-called knee of the luminosity function, objects that sit at the bright end of what's expected for their era. These are the easiest to detect, and they naturally look more impressive. But they're statistical outliers. If your telescope is biased toward the brightest objects, your first impression will always be skewed toward galaxies that look unusually developed for their time. Once Webb accumulates deeper, longer exposures over wider fields, the population begins to normalize. Early surveys always discover the flashy objects first. All of this leads to a simple takeaway. Mature appearance is not an age indicator in cosmology. It's an activity indicator. It tells you how vigorously a galaxy is forming stars, how dense its gas is, how quickly its halo grew, and how efficiently it's converting fuel into light. In the early universe, all of those factors can produce dramatic effects on very short timescales. So when people saw Webb's earliest galaxies and thought, these look too developed for their age, they were reading modern expectations onto ancient conditions. The early universe doesn't play by the rules we see today. It had its own physics, its own pace, and its own way of building structure. What looked like contradiction was really just misunderstanding. Understanding that difference removes the entire foundation of the older than the Big Bang narrative. These galaxies don't need more time. They need only the intense environment of the early cosmos, where gravity worked fast, matter was dense, and the first waves of star birth reshaped entire halos in the blink of a cosmic eye. One of the most persistent reasons people misinterpreted Webb's discoveries is that we don't use everyday language when we talk about cosmic time. Terms like age of the universe, look-back time, epoch, and cosmic age all sound similar, but in cosmology they mean very different things. When those differences got blurred in early discussions, it created space for headlines claiming Webb had found objects older than the universe. In reality, the mix-up came from people combining two separate timelines that were never meant to be merged. So let's untangle it in a way that doesn't require equations or a physics degree. Start with something simple. The universe is 13.8 billion years old. That number comes from measuring the expansion rate, the cosmic microwave background, and the distribution of galaxies. It's a well-tested value that dozens of methods converge on. When cosmologists say age of the universe, that's what they mean. The time that's passed since the Big Bang. But the light Webb sees from ancient galaxies didn't leave those galaxies today. It left them billions of years ago when the universe was much younger. That gap between when the light left and when we detect it is called look-back time. Look-back time can be almost the entire age of the universe. If Webb sees light that left a galaxy when the universe was 300 million years old, the look-back time is roughly 13.5 billion years. That doesn't make the galaxy 13.5 billion years old. It means the light has been traveling for that long. This difference might sound trivial, but it's actually the heart of the confusion. Look-back time isn't the age of the galaxy. It's the age of the journey its photons have taken. When you point Webb at a high redshift object, you're not seeing it as it is now. You're seeing it as it was at a particular moment in cosmic history. Here's where the misunderstanding spiraled. Some early reports mixed the look-back time with the galaxy's inferred age. For example, they'd say something like, "We're seeing a galaxy 13.5 billion years away," and then reinterpret that as, "This galaxy is 13.5 billion years old." But if the galaxy emitted 13.5 billion years ago, then it's not 13.5 billion years old. That light, when it was only 50 million years old, then its actual age at that moment was 50 million years, not 13.5 billion. You're just seeing it across a huge gap of time. Another layer of confusion comes from the way people think about distance in an expanding universe. In ordinary life, distance and time correlate. Something 10 kilometers away isn't also 100 kilometers away. But in cosmology, distance gets messy. A galaxy whose light has traveled 13.5 billion years didn't sit 13.5 billion light-years away when the light left. The universe has expanded during that journey. Today, that galaxy might be tens of billions of light-years away in proper distance, even though the look-back time is still 13.5 billion years. It's like watching a car drive away on an expanding road. The road stretches while the car moves, so its final distance isn't just the distance it drove. Misunderstanding this makes it easy to believe something paradoxical is happening, but nothing exotic is required to explain what Webb sees. A galaxy can have emitted its light 300 million years into cosmic history and still be around 33 billion light-years away today because space expanded in the interim. That doesn't violate relativity. That doesn't break cosmology. That's how general relativity says expansion works. Another part of the confusion came from how people interpreted early universe statements. When scientists said Webb found galaxies from 300 million years after the Big Bang, some people assumed that meant the galaxies were 300 million years old at that time. But after the Big Bang refers to the universe's age, not the galaxy's. The galaxy might have formed only a few million years before the light left. It didn't require long histories, it required rapid star formation under early universe conditions. And there's still another wrinkle. We never see early galaxies as they are currently. We see them frozen in their youth. A galaxy Webb sees at cosmic age 300 million years has, in reality, existed for the entire 13.8 billion year timeline since then. But we're not seeing that version of it, we're seeing the ancient version. It's like having a photograph of someone as a toddler and thinking that's their current age because the photo travelled a long distance to reach you. The travel time doesn't define the person's age, only the age of the snapshot. This is why cosmologists are extremely careful with phrasing. They distinguish from age of the universe at that moment. Look back time from now to when the light was emitted. The galaxy's age at the moment it emitted the light. These three values are related, but they are not interchangeable. When people mixed them in early reporting, it accidentally created statements that made galaxies sound older than the universe. One of the clearest examples of this happened when early photometric candidates were described as from 13.5 billion years ago. That phrasing was meant to convey the look-back time, but non-specialists interpreted it as an age measurement. So a galaxy that was maybe 40 million years old at the moment we're observing it was being described unintentionally as 13.5 billion years old. That's where the viral claims got their oxygen. Another point of confusion came from the way redshift was interpreted. People saw redshift numbers like 12, 13, 14 and assumed these must be ages because they're big numbers. But redshift is not a time measurement, it's a stretching factor. A galaxy at redshift 14 isn't 14 billion years old. It's emitting light from a period when the universe was a few hundred million years old. Redshift tells you how much the universe has expanded since that moment. It doesn't tell you the galaxy's age directly. Even some early scientific commentary added fuel to the confusion because phrases like too evolved for its time or too massive too early were interpreted literally. To a cosmologist, too early means earlier than simulations predicted, not earlier than the universe existed. But when those terms were taken outside context, they sounded like existential challenges to the entire Big Bang framework. Another subtle point. Galaxies don't all form at the same time. There was never a single switch-on moment. Different halos collapsed on different schedules, depending on density variations, seeded by quantum fluctuations. So when Webb sees a galaxy 300 million years after the Big Bang, that last detail doesn't mean all galaxies must have existed by then. It means that particular halo assembled and formed stars by then. Others took longer. The early universe wasn't synchronized. Understanding this helps explain why some Webb objects seemed too early. They weren't violating physics, they were simply forming at the earliest end of the distribution. Every distribution has outliers. Webb is just sensitive enough to detect them. One more reason that age confusion persisted is that humans intuitively think of time as absolute. But in cosmology, time depends on the reference frame, on expansion, and on the observer's vantage point. We aren't looking across a static stage. We're looking back along a path that stretches as the universe grows. What we see is a layered record of the past, not a set of ages stacked on top of each other. Once you separate look-back time from galaxy age, the entire older than the Big Bang narrative evaporates. It was never about galaxies actually being ancient. It was about the light from very young galaxies taking almost the full age of the universe to reach us. That's a profound thing, but not a paradox. It's exactly what we expect from a universe expanding for 13.8 billion years. Webb didn't show us objects that defy the cosmic timeline. It showed us how far we can reach into the universe's past when we look with the right kind of eyes, and how easily language can twist the meaning if we're not careful. Every time a new telescope opens a window into the universe, someone declares the Big Bang broken. It happened when Hubble found accelerating expansion in 1998. It happened when the first deep fields revealed galaxies farther away than anyone expected. It happened when Planck tightened the measurements of the cosmic microwave background. And it happened again as soon as Webb started showing us galaxies from the universe's first few 100 million years. Each time, the louder claims usually came from outside the scientific community, even though the actual scientists weren't abandoning the Big Bang. They were refining the early details. To understand why cosmologists weren't panicking about Webb's discoveries, it helps to look at what would have to fail for the Big Bang to be wrong. The Big Bang isn't based on one observation. It's based on a huge network of independent evidence that all points to the same origin. To overturn it, you'd have to break that entire network, not just one piece of it. Webb found some surprises in the early universe, but those surprises didn't touch the core pillars that make the Big Bang model work. Start with the most fundamental evidence. The universe is expanding. This was discovered by Edwin Hubble in the 1920s and later confirmed through redshift surveys, gravitational lensing, supernovae, baryon acoustic oscillations, and countless other tools. Expansion is a direct prediction of general relativity. Webb's observations depend on that expansion to interpret distances. In other words, Webb's entire mission relies on the framework that the Big Bang model established. If the universe weren't expanding, Webb wouldn't detect redshifts increasing with distance. But it does, precisely as predicted. Next, consider the cosmic microwave background. This is the leftover radiation from about 380,000 years after the Big Bang, when the first atoms formed and the universe finally became transparent to light. It's a nearly perfect blackbody spectrum with tiny fluctuations that match the seeds of early structure. Every galaxy Webb sees, no matter how early, must form after that moment. And that's exactly what we observe. Webb hasn't detected a single galaxy earlier than the cosmic microwave background. If galaxies appeared before that era, the entire map of the cosmic microwave background would be inconsistent. But it isn't. It lines up beautifully. Another key point is nucleosynthesis, the formation of the lightest elements in the first few minutes of the universe. The ratios of hydrogen, helium, and lithium predicted by the Big Bang match what we observe in the oldest stars and in intergalactic gas. For Webb to overturn the Big Bang, it would need to find galaxies made entirely of exotic elements or stars with elemental compositions that don't fit the early chemical recipe. But everything Webb has found so far fits neatly into the expected pattern. Even the signs of oxygen and other elements in early galaxies make sense. They come from massive stars, not from the Big Bang itself. There's also the matter of large-scale structure. When you map galaxies across the universe, they aren't randomly scattered. They form a cosmic web shaped by dark matter and early density variations. Webb's high redshift galaxies fall exactly where they should on that web. Their clustering, spacing, and distribution match what models predicted long before Webb launched. If the Big Bang were wrong, those patterns wouldn't line up. But they do across every scale Webb has examined. One reason scientists weren't worried is that none of Webb's discoveries contradicted these foundational pillars. What Webb did was highlight a specific area where predictions were incomplete, the speed and efficiency of early star formation. That's an important correction, but it's not a rewrite of the universe's origin. It's like discovering that human cities developed earlier in history than archaeologists expected. That changes the timeline of civilization, but it doesn't mean humans evolved earlier than we thought. It just means one part of the story was happening faster. The most accurate way to think about Webb's surprises is that they refine the beginning of the cosmic timeline, not the beginning of the universe itself. They show that structure emerged quicker, not that the universe itself started sooner. Those are completely different claims, and only one of them ever had evidence behind it. There's also a deeper reason the Big Bang isn't threatened. All the data from Webb fits comfortably within general relativity. The equations that describe how space expands, how matter collapses, how light stretches, and how time flows all continue to match observations. If the Big Bang were fundamentally wrong, Webb would have revealed inconsistencies in the expansion curve or distortions in the relationship between redshift and distance. Instead, the expansion behaves exactly as predicted. Another important detail is that the early universe was expected to be messy. For years, cosmologists knew that simulations had big uncertainties in the first few 100 million years. The physics of gas cooling, radiation feedback, halo mergers, and early star formation is enormously complex. Small changes in any of these processes can shift the timing by tens of millions of years. So when Webb showed galaxies forming sooner than predicted, it didn't break anything. It simply pointed to where the simulations needed better input. Scientists knew those early models would evolve once they had deeper data. In fact, one of the biggest signs that the Big Bang model is robust is that it continues to make accurate predictions even when telescopes improve dramatically. When theoretical models made 20 or 30 years ago laid out what early galaxies might look like, they anticipated smaller sizes, rapid evolution, and intense starbursts. Webb found exactly those things, just slightly earlier or more efficiently than older datasets hinted at. Another clear sign that cosmology isn't in danger is that the hydrogen reionization timeline remains consistent. The universe transitioned from neutral gas to ionized gas between redshift 6 and 10. Webb's detections of galaxies at redshift 12 to 14 fit perfectly into the expected ramp-up to reionization. These galaxies are simply showing that star formation was vigorous enough to contribute to ionizing hydrogen earlier than expected. But the timing still converges on a universe that becomes transparent in the same window the cosmic microwave background predicts. No contradiction. Even the most sensational early claims, like galaxies appearing too massive, lost their punch once better measurements came in. Updated mass estimates showed those objects weren't nearly as large as some early calculations hinted. New spectroscopic data revealed that many early candidates weren't at extreme redshift after all, and the ones that were truly high redshift fit comfortably within revised models that account for gas dynamics more realistically. Some people also speculated that dark matter must be behaving differently in the early universe. But as more Webb data has been analyzed, halo growth rates, gravitational lensing patterns, and structure formation all continue to match standard cold, dark matter models. Nothing exotic is needed. The universe simply forms bright objects quickly under dense conditions. A key thing to remember is that science welcomes challenges. If Webb had truly found a galaxy older than the cosmic microwave background, or an object at a redshift that makes no mathematical sense, cosmologists would have been the first to sound the alarm. But no such observation has happened. Claims that Webb found something older than the Big Bang were based on misunderstandings of how age, distance, redshift, and cosmic time are connected. There's also a broader philosophical point. Science doesn't treat models as sacred. If the Big Bang were wrong, scientists would abandon it. The only reason it survives is because it continues to match every test thrown at it. Webb wasn't designed to protect the Big Bang. It was designed to challenge it. And the fact that Webb's discoveries enrich the model instead of breaking it is a sign of its strength, not a sign of ignoring problems. One of the most compelling demonstrations that the Big Bang remains intact is that multiple independent Webb programs designed by different teams for different purposes keep converging on the same picture. Whether the researchers are studying early star formation, reionization, dark matter halos, or early black holes, the underlying timeline of the universe remains coherent. Disagreements happen over details, not fundamentals. Another way to see this clearly is to consider what Webb hasn't found. It hasn't found galaxies before the cosmic microwave background. It hasn't found stars with elemental compositions that contradict early nucleosynthesis. It hasn't found structures so massive that they can't grow in the time allowed by standard cosmology. It hasn't found anything at a negative age or which would be required to be older than the universe. These are the kinds of discoveries that would genuinely challenge the Big Bang. None have occurred. Instead, the true message from Webb is that the early universe was more dynamic and productive than older telescopes could reveal. Gravity acted fast. Gas cooled quickly. Dark matter halos merged efficiently. Massive early stars lit up galaxies in bursts. All of these are refinements to the story, not reversals. There's also the important point that the Big Bang model doesn't make rigid, day-by-day predictions about when the first galaxy should appear. It sets broad physical constraints, not exact timelines. The details depend on physics that is inherently chaotic: mergers, instabilities, local density variations, radiation fields. Webb's discoveries sit comfortably within those constraints. The early universe is pushing the edges, not breaking them. Perhaps the clearest reason cosmologists weren't alarmed is that the Big Bang is simply the best explanation we have for why the universe looks the way it does today. It explains the cosmic microwave background. It explains the abundance of elements. It explains the expansion. It explains large-scale structure. It explains high redshift galaxies. It explains why time and space behave the way they do. No alternative model explains all of those things simultaneously. In fact, no competitor model even comes close. And the few that have been suggested, like steady-state models, were ruled out decades ago because they failed to match basic observations like the cosmic microwave background. The Big Bang isn't just the dominant explanation. It's the only one that consistently matches reality. So when Webb surprised the world with galaxies shining earlier than expected, scientists didn't throw out the model. They did what science always does. They updated the details while keeping the structure that works. The Big Bang isn't a fragile idea that shatters under new data. It's a framework built on multiple pillars, and Webb's discoveries strengthen those pillars by filling in the gaps. Webb didn't break the Big Bang. It helped reveal a universe that started building itself almost immediately, fast, energetic, and bursting with creativity far earlier than we could see before. That's not a crisis. That's progress. Before Webb launched, the phrase "older than the Big Bang" already floated around online as a kind of shorthand for anything mysterious in cosmology. Once Webb started finding early galaxies, that phrase resurfaced, but almost no one stopped to think about what it would literally take to discover something older than the universe. It's a useful thought experiment because it shows just how dramatic such a discovery would have to be and how far Webb's actual findings sit from anything that extreme. Start with the basics. The Big Bang isn't just the beginning of matter, it's the beginning of time, space, and the physical laws we use to describe them. If something were older than the Big Bang, it wouldn't just be early, it would require a timeline outside the one the universe runs on. This isn't like finding a fossil that's older than scientists expected. This is like finding a fossil that predates Earth entirely. The scale of the mismatch would be massive, so what would it look like if we actually found something genuinely older than the Big Bang? In theory, there are only a few ways it could show up. One possibility would be light that's somehow older than the cosmic microwave background. The microwave background is the earliest light that the universe can produce after it becomes transparent, roughly 380,000 years into cosmic history. Anything older would have to come from a time when the universe was still a plasma, which should be impossible because light can't travel freely through that opaque phase. If Webb detected a clean, well-formed spectrum from before that era, it would rewrite physics instantly. But nothing like that has appeared. Every high redshift object Webb has found emits light consistent with post-recombination physics. Another scenario would involve galaxies at redshifts that don't make mathematical sense, objects whose redshift implies they existed before expansion even began. But redshift has a physical limit tied to the earliest moments where structure can form. In practice, galaxies can't exist at redshifts higher than the point at which matter becomes cool and stable enough to fall into halos. If Webb ever observed a galaxy at a redshift above that limit, it would signal a major breakdown in cosmology. Yet the highest confirmed redshifts so far stay within the expected range. They're surprising but not contradictory. They tell us galaxies formed rapidly, fast, not timeless. Another hypothetical signature of something older than the universe would be objects with chemical fingerprints that shouldn't exist yet. Heavy elements come from stars. Stars need time to form, burn, and explode. If Webb spotted a galaxy from the universe's first 100 million years containing large amounts of iron, gold, or other heavy elements that take multiple generations of stars to produce, that would force a dramatic reassessment. But the early galaxies Webb has observed don't show these kinds of chemical anomalies. The elements they contain, oxygen, carbon, maybe traces of neon, are exactly what you'd expect from the first massive stars. A more subtle sign would be structures too large or too smooth to fit into the timeline allowed by the Big Bang. If, for example, Webb identified a cluster of galaxies so enormous, so well organized and so mature that it couldn't have assembled in just a few 100 million years, then cosmologists would have a serious problem. But the early structures Webb is finding are compact and chaotic, not massive and orderly. They're the cosmic equivalent of construction sites, not finished skyscrapers. They form quickly but still obey the rules of gravitational growth. Another possible smoking gun would involve objects with negative ages, meaning their inferred ages exceed the age of the universe at the moment their light was emitted. That's the scenario some influencers hyped early on. They heard that certain galaxies looked too old for their epoch and ran with it. But the initial claims reversed the logic. These galaxies weren't old, they were young but bright. They didn't challenge the universe's age, they challenged assumptions about how fast gas can collapse and how efficiently stars can form. Once better measurements came in, the mass and age estimates dropped into perfectly normal ranges. There's also the idea of a cosmic relic from a previous universe, something left over from a before state. In theory, if the universe goes through cycles, or if multiple universes collide, there could be imprints or scars. Some researchers suggested that concentric circles in the cosmic microwave background might be evidence for earlier cosmic cycles. But even the strongest advocates of those ideas never suggested galaxies came from before the Big Bang, and Webb has not observed anything remotely like a pre-universal object. The early galaxies fall along the expected timeline shaped by the Big Bang's aftermath. Another angle involves physics constants changing. If the speed of light, gravity, or other constants were different in the early universe, that could distort age estimates. But Webb's data continues to match constants measured in other regimes. The physics seems consistent from the earliest galaxies to nearby ones. No numbers drift, no laws break. If something were older than the universe, we'd expect to see those kinds of cracks first. So when you actually list out the signatures of a pre-Big Bang object, the bar is extremely high, and Webb hasn't found anything even close. What it has found are galaxies forming at the earliest allowed moments. Not before, not against the rules, just fast. In fact, one of the most interesting things Webb has shown is how deeply our expectations were shaped by older telescopes that simply couldn't see faint early objects. When Hubble pushed the frontier, it found galaxies at redshift 7, 8, 9. Some scientists suspected there might be galaxies even earlier, but Hubble couldn't catch them. Webb did. And once it did, it became clear that early galaxy formation starts almost as soon as the physics allows it to. This is where the big misunderstanding lies. Earlier than expected is not the same as impossible. The early universe is dense, energetic, and chaotic. Small halos collapse quickly. Feedback from massive stars is extreme. Star formation can happen in bursts. If there's enough gas and enough dark matter halo structure, a galaxy can go from nothing to shining intensely in a few tens of millions of years. That's fast, but it's not magic. It's physics operating under extreme conditions that we're only now able to see clearly. The other thing that fuels these misunderstandings is how humans visualize the universe. We tend to imagine the Big Bang as a bright flash, like fireworks, followed by darkness and slow build-up. But the universe didn't behave like a fireworks show. It behaved like a pressure cooker. Conditions were primed for quick structure formation as soon as temperatures dropped enough to let gravity take over. That means galaxies could appear rapidly without violating the cosmic timeline. Another factor is that early galaxies don't need long, stable histories to shine. In the modern universe, galaxies often take their time building mass. They grow slowly, evolve gradually, and stretch their star formation over billions of years. But early galaxies are a different species entirely. They're turbulent, dense, heavily influenced by dark matter, and capable of forming giant stars at breakneck speed. A galaxy that looks too bright for its age is usually just a galaxy with a lot of massive, short-lived stars lighting it up. Some people also misunderstood how size and brightness relate. A galaxy doesn't need to be huge to be bright. In fact, many of Webb's early galaxies are tiny compared to modern galaxies, sometimes just a few hundred light-years across, but filled with young stars burning intensely. When you cram that much star formation into such a small volume, the galaxy shines like a torch. But that brightness has nothing to do with age. It has everything to do with density. There's also a psychological reason these misunderstandings spread. The Big Bang is iconic. People like the idea of it being challenged. Headlines love drama. A galaxy forming sooner than expected doesn't grab attention. A galaxy older than the universe does, even if it's not true. The gap between scientific language and public interpretation gives these dramatic claims plenty of room to grow. If Webb had truly found something older than the Big Bang, cosmologists wouldn't be politely debating details. They'd be publishing emergency papers. Conferences would reorganize entire agendas. Theoretical physicists would be scrambling to build new frameworks. But none of that has happened. What has happened is intense, focused effort on refining the early chapters of cosmic evolution, exactly what a new telescope is supposed to trigger. And there's a deeper reason no crisis emerged. Webb's discoveries align with other independent lines of evidence. The cosmic microwave background still tells a consistent story. Large-scale structure still fits the expected pattern. Element abundances still point to the same early conditions. The expansion history still follows the same curve. These big picture checks act like anchors. When new observations come in, they either tie into the existing framework or break it. Webb's do tie in. They stretch it in places, but they don't snap it. So the real headline isn't that Webb found objects older than the Big Bang. It's that Webb finally showed us the early universe operating at full speed, forming stars and galaxies as soon as physics allowed it. If you picture the cosmic timeline as a race, these early galaxies aren't cheating. They're just sprinting from the moment the race starts. What we're learning isn't that the universe is older than we thought. It's that the universe wasted no time getting to work. If there's one part of Webb's early data that genuinely surprised scientists, not in a break the universe way, but in a we need to rethink the details way, it's the speed at which the very first stars appeared and started transforming their surroundings. These stars, often called population 3 stars, were supposed to be rare and elusive. They were made almost entirely of hydrogen and helium, with none of the heavier elements that later stars inherited. Their formation marks the moment when the universe went from darkness to light, and from simplicity to complexity. Before Webb, we had only models describing this period. The physics was built on the idea that gas cooling would be inefficient, halos would grow gradually, and early star formation would take its time ramping up. In that picture, the first stars might start forming around 100 to 150 million years after the Big Bang, but bright, organized galaxies would take longer to appear. But Webb's early deep field observations showed something different. Star formation wasn't just happening early, it was happening fast. Fast enough for some galaxies to already look surprisingly bright just a couple hundred million years into cosmic history. That doesn't mean these galaxies were old, it means they were efficient. To understand why this matters, it helps to look at what conditions were like in the early universe. Right after recombination, the cosmos was mostly smooth, with small fluctuations in density. These tiny variations eventually grew to become the large-scale cosmic web, but growth takes time. Gravity doesn't work instantly, it pulls matter together over millions of years. That's why earlier models predicted a gradual rise in star formation. But recent simulations and better data, now cross-checked with Webb, show that the earliest regions weren't uniform. Some pockets had higher densities than average, giving them a head start. These dense pockets collapsed into halos faster, allowing gas to pile up early. Under the right conditions, large clouds of pristine hydrogen could cool enough to collapse into massive stars in surprisingly short bursts of time. But here's where things get interesting. Pristine hydrogen cools differently than enriched gas. In modern galaxies, metals help radiate away heat, encouraging gas to clump and form stars. Without those metals, cooling is slower. So for a long time, researchers assumed that population 3 stars would form only in small numbers, and that it would take a while for star formation to become efficient. Yet Webb's data hints that the earliest gas clouds might have cooled faster than expected because of how radiation and turbulence interacted in those dense regions. Massive early stars, much larger than most modern stars, produce intense ultraviolet radiation. That radiation can heat surrounding gas, but it also creates shock waves that compress nearby regions, triggering more star formation. So instead of slow, steady buildup, early star formation looks more like chain reactions. One region collapses, ignites, and pressures nearby gas into forming stars of its own. Another factor is the behavior of dark matter halos. Early on, halos merged rapidly. Each merger dumped new gas into the system, creating small starbursts. These bursts didn't need to last long to produce the kind of light Webb detected. Even a brief period of intense star formation could make a young galaxy appear brighter than expected. But nothing about this challenges the cosmic timeline. It just means the universe was more dynamic than older models assumed. The early cosmos wasn't a calm, gradual environment. It was turbulent and energetic. There's also a key difference between early star formation and what we see in modern galaxies. Today, galaxies are large, complex systems with dust, magnetic fields, evolved stars, and long-term star formation cycles. Early galaxies were tiny, simple, and raw. Without dust or heavy elements to absorb light, the radiation from early stars escaped far more efficiently. From our point of view, that means a little star formation went a long way. A galaxy with a few 100,000 massive stars could outshine a much larger modern galaxy. This helps explain why some of Webb's earliest detections looked surprisingly bright. It wasn't that the galaxies were huge or ancient. It was that the ingredients and physics of early star formation made brightness easier to achieve. The other major clue comes from what Webb sees in the spectra of early galaxies. Many of them show a strong ultraviolet slope that indicates hot young stars. Others show signs of ionized gas, suggesting bursts of star formation only a few million years old. And some appear so compact that they're barely more than giant star clusters. These are not galaxies with long, drawn-out histories. They're newborn systems, lighting up quickly and intensely. One of the most intriguing questions now is whether Webb will ever catch a pure population 3 star system, a group of stars with no heavy elements at all. Those would be the literal first generation. We've never seen them directly. Every time we look at early galaxies, we detect traces of oxygen or carbon, meaning at least one earlier generation of massive stars must have already lived and died. That tells us early star formation cycles were fast enough that even the earliest galaxies Webb can see have been processed at least a little. Finding a truly pristine object is now one of Webb's major goals. If such a system exists, it should sit right at the boundary between the universe's first few tens of millions of years and the onset of the first bright galaxies. And if Webb finds one, it will help answer some of the biggest open questions in early cosmology. How massive the first stars were, how they exploded, and how quickly they enriched the universe with the first heavy elements. And that's where the real mystery sits. Not in the idea of galaxies older than the Big Bang, which never happened, but in how quickly the universe transitioned from simplicity to complexity. The jump from darkness to starlight wasn't a gentle ramp. It was a sudden ignition. Gravity, radiation, and chemistry combined to light up the cosmos far faster than humans once assumed. Yet everything Webb has seen still fits within the Big Bang storyline. The excitement comes from filling in details we've never had access to before, not from breaking the timeline. The more Webb looks, the more it shows that the universe didn't wait around to become interesting. It started building structure the moment it had the chance, and the first stars may end up being even more extreme than scientists once imagined. When most people imagine black holes, they picture the monsters at the centers of modern galaxies, millions or billions of times the mass of the Sun, built up over billions of years of mergers and feeding. For a long time, that timeline made sense. Start with small stars, make small black holes, let them merge and gradually gather enough material to become supermassive. Slow, steady growth across cosmic time. But Webb's findings threw a wrench into that picture, not because they suggest something impossible, but because they show that black holes didn't wait around. They appeared early, grew quickly, and shaped the first galaxies far more aggressively than older models anticipated. And this is one of the biggest real mysteries emerging from Webb's observations. Not older than the Big Bang nonsense. Not anything that breaks cosmology. Just a puzzle about how efficiently nature can build extreme objects in the universe's first few 100 million years. The basic problem goes like this. Black holes need fuel to grow. In the early universe, that fuel is gas, dense, cooling hydrogen flowing into the first halos. If a black hole starts small, say with the mass of a large star, it has to eat continually to reach supermassive sizes quickly. But early galaxies are messy and chaotic. Gas can be blown away by intense star formation or heated by radiation. So models once predicted that early black holes would grow slowly, gaining mass over long stretches rather than huge bursts. Webb's early data doesn't exactly contradict that, but it challenges the idea that slow growth is the default. Black holes in some of Webb's high redshift galaxies appear surprisingly massive for the time available. Not impossibly massive, but big enough that you can't assume they started small. That led to a renewed interest in the idea of direct collapse black holes. Black holes born large, not grown large. The logic behind direct collapse is straightforward. If a huge cloud of pristine gas collapses without breaking into stars first, the entire cloud could collapse into a massive black hole, maybe tens of thousands of solar masses right from the start. That gives you a big head start. Instead of a stellar mass seed trying to eat its way upward, you start with a massive seed that only needs moderate, steady feeding to grow. Before Webb, this idea was mostly theoretical. Now, the brightness and structure of some early galaxies make it harder to dismiss. These aren't galaxies that evolved for hundreds of millions of years. They're young, chaotic, and full of dense gas, conditions where direct collapse seeds start to make more sense. But even if black holes didn't start large, the environment around them was incredibly favorable for fast growth. High-density gas, high merger rates, and short cooling times created feeding opportunities that modern galaxies rarely see. Early black holes might have eaten in bursts, growing in short but intense episodes where gas funneled directly into the center. And because there was little dust, the radiation from all that feeding escaped easily. That makes early black holes easier for Webb to detect than previously thought. They shine brightly in the ultraviolet and infrared because the material around them heats up to extreme temperatures. But the real surprise comes from how active early galaxies appear. Many of the youngest galaxies Webb has observed show hints of energetic cores, places where black holes might already be influencing their surroundings. They produce ionized gas, unusual emission lines, or compact bright centers. Not every bright core is a black hole, but the pattern suggests that black holes were participating in galaxy evolution earlier than predicted. In the old picture, stars dominated the early galaxy landscape and black holes caught up later. Webb suggests the two stories were intertwined from the beginning. Another key piece of evidence comes from the shapes of early galaxies. Many of them are small, dense, and extremely compact, just a few hundred light-years across. When galaxies are that tightly bound, black holes can interact with the entire system more easily. A black hole that accretes gas in such an environment can drive powerful winds or radiation that affect star formation. This connection between early black holes and early starbursts hints at feedback happening almost immediately. That's important because feedback, black holes heating or blowing out gas, shapes how galaxies grow. And if feedback starts earlier, we have to rethink how quickly galaxies settle into stable structures. But this isn't a crisis, it's a refinement. The early universe simply gave black holes better growth conditions than modern galaxies do. There's no contradiction in that. It's like comparing a seed planted in nutrient-rich soil with one planted in dry sand. The environment matters. The early universe was the cosmic equivalent of a greenhouse. To see how black holes might have formed so early, imagine the timeline from recombination onward. The universe cools. Gas flows toward the densest spots. Small halos collapse first, pulling in hydrogen. If the gas density is high enough and cooling is efficient enough, stars form. If not, gas keeps collapsing. In some cases, the collapse might avoid fragmenting into stars entirely. That's when direct collapse black holes become possible. These large black hole seeds then start shaping their environment, generating radiation that helps or hinders further star formation. Another path involves massive early stars. Population 3 stars, if they exist the way models suggest, would be huge, perhaps hundreds of times the mass of the Sun. When they end their lives, they collapse into black holes. If a dense environment funnels gas toward them, they could grow quickly. Webb's observations don't directly reveal these first stars, but its detection of early galaxies with young, hot stellar populations suggests the conditions needed for massive stars were present. But one of the biggest clues comes from spectra. Some of the earliest galaxies Webb studied show emission patterns that look a lot like what you'd get from gas heated by an active black hole, rather than just by stars. These are small systems, so the black holes don't need to be enormous. A few 100,000 solar masses might be enough to dominate the galaxy's center. That's not supermassive by today's standards, but it is large for the early universe. The more Webb looks, the more it finds hints of activity where older telescopes saw only faint smudges. Still, none of these findings challenge the overall cosmological timeline. They challenge the details of early astrophysics. They show that black holes didn't grow politely or slowly. They grew opportunistically, taking advantage of dense gas, rapid mergers, and the fact that the early universe was small enough that everything was closer together. Feeding was easier, collisions were more common, gas was more available. What's interesting is how this affects our understanding of early galaxy formation. For years, the narrative was simple. Stars formed first, galaxies grew gradually, and black holes emerged later. Now, it looks like black holes and stars grew together, with black holes acting as engines that sped up or slowed down star formation on short time scales. That feedback loop might explain why some early galaxies look extremely bright, while others look unexpectedly faint. In some cases, a black hole might heat the surrounding gas and slow star formation. In others, its radiation might compress nearby gas and trigger more star formation. It also explains the variety of structures Webb sees. Some early galaxies are smooth and compact. Others are clumpy. Some are dominated by bright cores. Others look like scattered knots. If black holes were shaping how gas moved in these early systems, the diversity makes sense. It's not that the early universe was chaotic in a meaningless way. It was chaotic because gravity and radiation were competing constantly. This is why early black holes matter so much. They're not an isolated puzzle. They link directly to how galaxies formed, how stars emerged, how gas cooled, and how the universe reionized. If black holes were active earlier than expected, they may have contributed to heating and ionizing the universe, helping to lift it out of its neutral state faster than stars alone could. That might explain some of the early ionization signatures Webb has detected. There's also the deeper question of growth rates. Black holes can only grow so fast before radiation pressure pushes back, limiting how much gas can fall in. This limit is called the Eddington limit. For years, scientists assumed black holes in the early universe couldn't exceed this limit for long, but fresh simulations suggest that in dense, chaotic environments, black holes might temporarily exceed it. If that's true, then even small seeds could grow rapidly under the right conditions, helping bridge the gap between early black holes and the supermassive ones we see 700 million years after the Big Bang. This whole picture also connects to one of the biggest open questions: how the first quasars formed. Quasars, bright cores powered by massive black holes, appear very early in the universe, and some of them already contain black holes 1 billion times the mass of the Sun, less than 1 billion years after the Big Bang. Webb isn't built to focus on quasars specifically, but its measurements of early black hole activity help fill in the timeline leading up to them. If black holes were growing aggressively at redshift 10 or higher, then reaching 1 billion solar masses by redshift 6 becomes more plausible. None of this says the early universe was older than we thought. Instead, it's telling us something more interesting. The early universe was more efficient at building extreme objects than older models predicted. There's a temptation to assume that faster formation means a problem with the timeline itself. But the physics behind star formation, gas collapse, and halo mergers is flexible. It allows a range of outcomes depending on density, temperature, and environment. Webb is simply revealing which parts of that range nature actually used. One of the reasons this field is exciting right now is that we're seeing the earliest stages of galaxy and black hole co-evolution directly, not just as faint hints. Webb's infrared sensitivity allows it to cut through dust and catch the glow from gas that's heated by intense processes. And because it can analyze the light with fine detail, it can distinguish between gas heated by stars and gas heated by black holes. That's the level of detail needed to understand how these objects grew together. The big takeaway is that early black holes aren't cosmic anomalies, they're cosmic accelerators. They sped up the universe's early evolution by adding energy, shaping gas flows, and compressing or clearing regions of star-forming material. Their presence explains phenomena that once seemed surprising. They don't break the timeline, they help fill in the timeline. Webb is teaching us that galaxies didn't just appear. They assembled quickly under extreme conditions, and black holes were part of that assembly from the beginning. The earliest black holes aren't problems to solve, they're clues to how the universe figured out how to build complex structures in a remarkably short time. When you hear about ancient galaxies and fast-growing black holes, it's easy to imagine the early universe as a dark arena dominated by gravity alone. But the real engine of that era, the thing shaping chemistry, heating gas, and setting the pace for galaxy formation, was the first generation of stars. And Webb's observations keep showing that these early stars formed faster, burned hotter, and influenced their surroundings more intensely than older models predicted. This isn't about rewriting the age of the universe, it's about understanding why the first few 100 million years were so productive. To understand that productivity, you have to picture what star formation meant when the universe was young. The gas back then was incredibly simple: hydrogen, helium, and nothing heavier. Without elements like carbon or oxygen, gas couldn't cool efficiently. And if gas can't cool, it can't collapse into small, orderly clumps. So the first stars weren't like the Sun. They were probably enormous, hundreds of solar masses in many cases, and they lived fast. Their cores reached higher temperatures because the gas was pristine. Their radiation was more intense because their surfaces burned hotter. And when they finally died, they didn't fade quietly. They went out with enough energy to reshape entire galaxies. Webb hasn't seen these first stars directly yet. They're too faint and too short-lived. But it has picked up galaxies filled with unusually hot, blue stellar populations that behave exactly the way you'd expect if those galaxies were still carrying echoes of the first stars. The light from these systems is dominated by high-energy ultraviolet radiation, which tells us the stars inside are young and massive. You don't see that kind of light from old metal-rich stars. You see it when stars form quickly in an environment where nothing has had time to enrich the gas. That's why early galaxies look so compact and bright. There's a burst of star formation happening in a very small volume. One of the biggest clues that early stars were different comes from unusual emission lines Webb keeps detecting. These lines appear when intense radiation strips electrons off atoms. In some early galaxies, the gas is so ionized that it looks more like the output of giant stars or hot black hole accretion disks than quiet star-forming clouds. Even if you assume the stars are massive, hot, and packed tightly together, the amount of ionization still pushes the limits of older models. That's why scientists are taking seriously the possibility that massive population 3 stars, those first metal-free giants, might still be influencing the galaxies Webb is observing at high redshift. But the role these early stars played goes far beyond lighting up their galaxies. They set the chemical baseline for everything that followed. When these stars died, they seeded their surroundings with heavier elements. This didn't happen gradually. It happened in enormous bursts when the stars ended as supernovae. These explosions pushed enriched gas out into the surrounding medium, and that enriched gas cooled more efficiently than the pristine hydrogen it replaced. Once gas could cool more easily, smaller stars emerged. That shift from massive, metal-free giants to more ordinary stars helped stabilize galaxies. It created a pathway for long-lived stars like the Sun. It created planets. It laid the groundwork for chemistry we now think of as normal. What Webb has done is compress that entire timeline. Before Webb, the common view was that this transition from early massive stars to more typical stars took place gradually over hundreds of millions of years. But Webb keeps finding galaxies that already contain elements heavier than helium, far earlier than expected. That means the first generation of stars lived and died faster. They enriched their environments more quickly, and they kicked the universe into a higher gear. Another aspect that's becoming clearer is how tightly the life cycle of these stars was linked to galaxy structure. Early galaxies weren't stable disks with orderly spiral arms. They were small, dense pockets of gas undergoing constant collisions and mergers. When 2 small galaxies collided, the gas inside them compressed violently, triggering bursts of star formation. Those bursts were so intense that the stars inside them influenced each other directly. Radiation from one cluster could heat or disrupt nearby clouds, altering the timing of new star birth. Every small galaxy was essentially a laboratory where gravity, gas, and radiation were locked in constant competition. One reason this competition was so intense is that early galaxies didn't have much volume. Many were only a few hundred light-years across. That's tiny compared to modern galaxies, and it means energy couldn't scatter easily. If a massive star produced powerful winds, those winds didn't spread out gently. They slammed into nearby gas clouds and either triggered new star formation or blew material out of the system entirely. This back-and-forth feedback explains why early galaxies appear so clumpy in Webb's images. They're young systems trying to regulate themselves without the large-scale structure that stabilizes galaxies today. The other surprising element in Webb's early data is that star formation didn't seem to taper off in these tiny systems. Once the cycle started, it kept going. That tells us the gas supply was continuous. Dark matter halos, the invisible gravitational wells in which galaxies form, were pulling in fresh hydrogen constantly. Every time a galaxy used up or expelled gas, new gas streamed in and replaced it. That supply line kept star formation running at a pace modern galaxies rarely achieve. The Milky Way today forms only a few solar masses of stars per year. Some of the early galaxies Webb sees at high redshift appear to have been forming stars at a rate dozens or even hundreds of times higher, despite being a fraction of the size. That difference in scale shows how conditions shaped star birth. High density meant faster collapse. Low metallicity meant hotter gas. Frequent mergers meant repeated starbursts. And the lack of dust meant radiation could escape more easily, which gives Webb a clear view of what would otherwise be hidden. Because these environments were extreme, the stars themselves would have been extreme by modern standards. They likely spun faster. They burned through their nuclear fuel more quickly. Their winds were stronger, and their lifetimes were short, sometimes only a couple of million years. That's nothing on a cosmic timeline. From a storytelling perspective, it's tempting to say these stars built the early universe, but the reality is even more interwoven. They built it, and they destabilized it at the same time. Their radiation carved out cavities in the gas. Their winds swept material away from star-forming regions. Their supernovae blasted shockwaves through galaxies. Each destructive process created new pockets of formation elsewhere. The universe wasn't building peacefully, it was building in cycles of compression and disruption, all happening on short timescales. And this is exactly the environment where black holes and galaxies grow together. Another major insight from Webb's early data involves reionization, the era when the universe transitioned from neutral gas to ionized gas. For years, the big debate was whether stars or black holes played the main role. Did starlight ionize the universe, or did early black hole accretion do it? Webb is revealing that the answer is not either-or, it's both. The sheer number of early hot stars in these compact galaxies means they produced enormous amounts of ultraviolet light, far more than older telescopes detected. That makes them major contributors to ionization. But the pattern of ionization in some galaxies is too strong to be explained purely by stars. Something else, likely early black hole activity, contributed too. This combined influence helps explain why ionization happened faster than expected. The universe didn't rely on one mechanism. It used every tool available. Hot stars ionized their immediate surroundings. Black holes ionized gas in more focused but intense regions. Supernovae cleared pathways through which radiation could travel. And mergers constantly stirred gas and exposed new pockets. When scientists say the universe ionized, it's easy to picture this as a smooth transition. Webb's data makes it clear it was anything but smooth. It was irregular, patchy, and driven by structures forming rapidly. Another unexpected detail is that early galaxies often show signs of internal mixing. This means supernova-enriched gas didn't stay localized. It circulated, helping reset conditions quickly. Without efficient mixing, it would take much longer for galaxies to accumulate the heavier elements needed to cool gas. But with rapid mixing, the transition from massive population 3 stars to more ordinary stars could happen surprisingly early. That's exactly what Webb's early spectral data suggests. Something else Webb has helped clarify is how quickly small galaxies merge to form larger ones. The older view held that early galaxies evolved slowly into the larger structures we see today. But the sheer number of small, bright, chaotic galaxies in Webb's images implies a high merger rate. This matters for star formation because mergers compress gas. They're triggers. Each collision creates an opportunity for new starbursts, and each starburst leaves behind new chemical signatures. You can track these signatures like layers in a rock formation. The earliest layers show pristine gas. Later layers show metals, and the timeline between them turns out to be short. This rapid enrichment helps solve several problems at once. It explains why galaxies only a few 100 million years old already show signs of second-generation and third-generation stars. It explains why the early universe was able to form complex structures quickly, and it explains why some early galaxies appear brighter than expected for their age. Brightness doesn't always mean size. Sometimes it simply means the stars inside are unusually hot and dense. One of the most intriguing consequences of this rapid enrichment is how it affected planet formation. You can't form rocky planets without heavier elements like silicon, oxygen, and iron. These elements come from massive stars exploding. The faster those stars lived and died, the sooner the universe produced the chemistry needed for planets. That doesn't mean early galaxies hosted Earth-like planets. conditions were too chaotic. But it does mean the timeline for creating the necessary ingredients started earlier than once assumed. Webb's contribution here is its ability to detect faint signatures of heavy elements in galaxies that existed when the universe was less than 500 million years old. That doesn't rewrite cosmology. It tightens the story. It says the first stars didn't just appear quickly, they burned through their life cycles quickly enough to kickstart chemical evolution in record time. What ties this entire chapter together is the idea that early stars weren't placeholders waiting for galaxies to mature. They were active agents shaping structure, chemistry, and energy distribution across the universe. Their influence wasn't limited to their own galaxies. Their radiation leaked into the intergalactic medium. Their supernovae seeded nearby halos. Their winds reshaped gas flows. They were the universe's first machines, simple in composition, extreme in behavior, and crucial for everything that followed. And Webb's observations keep revealing just how efficient these machines were. If you followed any Webb headlines over the past couple of years, you've probably seen the phrase "older than the Big Bang" thrown around like it's a normal thing to say. It's not. Nothing Webb has found is literally older than the Big Bang. What is happening is more subtle. Webb keeps finding galaxies, stars, and black holes that look surprisingly mature for their age, and people confuse mature with old. Those two ideas are not the same, especially in cosmology. Before Webb, the earliest galaxies we expected to see were small, dim, and relatively simple. They'd be in the process of assembling themselves, not in the business of shining like fully developed systems. Simulations suggested that significant structure would take hundreds of millions of years to emerge. The Big Bang happened 13.8 billion years ago. Structure formation didn't get going until the universe cooled enough for gravity to start pulling things together. That left only a small window for extremely bright or well-organized galaxies to form. Then Webb arrived and immediately started upsetting those expectations. The telescope wasn't finding impossible galaxies, it was finding galaxies that seemed to sit right at the edge of what the models allowed, and sometimes a little beyond. Instead of messy clumps of gas barely starting to glow, Webb was picking up objects that looked unusually dense or bright for their redshift. And that raised an obvious question. How did these structures form so quickly after the Big Bang? Some early interpretations jumped to dramatic conclusions. If these galaxies looked older than they should, maybe they really were older. Maybe the universe was older than we thought. Maybe the Big Bang model needed to be replaced. And from there, the internet did what it usually does. It amplified the wildest version of the story. If you strip away the hype, what Webb is showing is actually straightforward. The early universe was efficient. It built stars faster, grew black holes faster, and assembled dense galaxies faster than some models predicted. But efficiency doesn't equal age. Efficiency means the timeline was busy, not stretched. The reason this distinction matters is because age and appearance don't scale the way people assume. A galaxy doesn't need 1 billion years to become bright. It needs gas, density, and a rapid sequence of starbursts. If it forms stars at 10 times the rate of a modern galaxy, it can look grown up in a fraction of the time. And that's what Webb is catching. Not ancient galaxies, but galaxies running on overdrive. Another important factor is observational bias. Older telescopes like Hubble were good at spotting large, bright structures, but they struggled with extremely distant, faint ones. Webb's infrared sensitivity changes that. It sees objects Hubble couldn't detect, including compact galaxies that were invisible before. When people say Webb found too many early galaxies, part of the issue is that we're seeing populations that were always there, we just didn't have the tools to detect them. You can't claim something is unexpected if you only had half the picture before. There's also a subtle point about redshift. Redshift tells us how long the light has been traveling, not how mature the galaxy was when it emitted that light. When Webb detects a galaxy at, say, redshift 12, that means we're seeing it as it existed around 350 million years after the Big Bang. That's the timestamp. But whether it looks like a small baby galaxy or a surprisingly bright system depends on how fast its stars formed, how tightly its gas collapsed, and how often it merged with neighbors. A galaxy can look developed while still being very young, just like a human teenager can look tall without being old. This misunderstanding is what feeds the headline "older than the Big Bang." The objects that look surprisingly bright or massive are still exactly where they should be on the timeline. They're simply behaving at the upper end of what physics allows, not breaking the timeline itself. And here's where the deeper story becomes interesting. These mature early galaxies are teaching us that the early universe wasn't empty, calm, or slow. It was crowded. It was dense. Gravity was intense. Gas cooled quickly. Mergers were constant. Black holes were hungry. And stars were huge. If you put all of that together, you get a universe that builds galaxies far faster than the modern one. We're used to the slow pace of the Milky Way, which forms a few suns worth of stars every year. But early galaxies formed hundreds of suns worth. A tiny galaxy could go from a gas cloud to a glowing bright object in a few tens of millions of years. In cosmic terms, that's instant. Another reason these galaxies look old is because of the types of stars they contain. Massive stars burn hot and bright. If you fill a galaxy with them, it looks spectacular early on. But these stars die quickly, so you can have a galaxy that looks incredibly luminous without it being old at all. It's bright not because it's ancient, but because it's packed with short-lived stars that produce intense ultraviolet radiation. Webb is also catching galaxies that seem unusually compact. Some are only a tiny fraction of the size of the Milky Way, but produce comparable light output. That compactness boosts brightness. It doesn't mean age, it just means density. In the early universe, density was easy to achieve. Everything was closer together. Gas didn't have to travel far to collapse. Dark matter halos were small but packed. This is exactly the environment that would produce overachieving galaxies. But perhaps the biggest misconception is that the Big Bang model requires early galaxies to be dim. It doesn't. The Big Bang model sets the timeline. When the universe expanded, when it cooled, when matter formed. It doesn't dictate how efficient galaxies must be. That's astrophysics, not cosmology. The structure formation models we used before Webb were based on simulations that made assumptions, reasonable ones at the time, but still assumptions. When new data arrives, models shift. The timeline stays intact. This is how science works. Models aim to predict. Observations correct the predictions. You adjust the model to include faster star formation, or more efficient gas cooling, or heavier early black hole seeds. You don't throw out the entire Big Bang unless you find something that breaks the core physics, like matter moving faster than light, or a structure physically older than the expansion itself. Webb has found nothing like that. The truth behind the headline is almost always this: an early galaxy looked brighter or more massive than the old models expected. That's it. That's the whole story behind the scary phrase, older than the Big Bang. What makes this moment exciting isn't that cosmology is breaking, it's that astrophysics is being rewritten. The early universe wasn't a gentle ramp-up from simplicity to complexity. It was a sprint. It built structures quickly because conditions allowed it. And Webb finally has the sensitivity to watch those first steps in detail. The irony is that when we see a galaxy that looks too developed for its age, that object is actually doing us a favor. It's telling us exactly where our models were too conservative. It's marking the spots where nature was more aggressive than expected. These galaxies aren't mistakes. They're milestones. They're showing us the true pace of the universe's earliest growth. And now that Webb has revealed how fast things really moved, the next big question is how these early structures linked up to build the large-scale cosmic web we see today. A transition that wasn't smooth, wasn't slow, and definitely wasn't predictable before the data arrived. When astronomers first looked at Webb's earliest deep-field images, a few galaxies stood out immediately. They were tiny points of light, barely distinguishable from noise. But when the spectra came back, the numbers forced everyone to take a step back. These galaxies were extremely distant, so distant that their light had been traveling for more than 13 billion years. And yet they weren't faint, they weren't small, they weren't barely formed. They looked busy. That word busy is doing a lot of work, but it's the most honest way to describe them. They were forming stars at an intense rate. Their stellar populations looked surprisingly mature for their age. Some even hinted at early black hole activity. This mix, dense stars, fast formation, bright output, created the impression that they had no right to exist so soon. And that impression is what powered all the headlines, claiming something must be older than the Big Bang. But when you go through the data carefully, the actual takeaway is almost the opposite. These galaxies don't break the Big Bang model at all. They confirm parts of it, refine others, and challenge the way simulations envisioned the early universe. Not the age of the universe, not the expansion timeline, just the details of how matter behaves under extreme density and youth. To understand why the galaxies looked impossible, it helps to start with the assumptions baked into earlier models. A lot of pre-Webb simulations made conservative guesses about early star formation. They assumed that gas in the young universe cooled slowly because it didn't contain heavy elements. They assumed that early halos weren't dense enough to collapse extremely fast. They assumed that small galaxies formed stars inefficiently and that mergers took time to build brighter systems. These were logical assumptions for a period of cosmic history we'd never directly observed. But many of those assumptions were based on the limitations of older telescopes. Hubble could see the brighter early galaxies. It couldn't detect the faint ones or the extremely small ones that filled out the rest of the picture. When your data is skewed toward the brightest outliers, you unconsciously model the universe in a way that matches those outliers. Webb, by contrast, sees almost everything: faint galaxies, compact galaxies, oddly bright galaxies, chaotic clusters, diffuse systems, and tiny galaxies that act like they're running on caffeine. One of the first things Webb made clear is that early star formation wasn't slow. Gas was denser back then. Halos were closer together. Cooling could happen through molecular hydrogen, not just heavier elements. That alone shortens the timeline for the first stars. If your baseline assumption is slow, seeing fast feels like a contradiction. But if the actual physics allowed rapid collapse from the beginning, as the new data suggests, then nothing is violating the rules. Another reason the early galaxies look intense comes from their star populations. When you pack massive, hot stars into a compact space, you get extreme brightness per unit volume. A small galaxy that forms stars in a rush will look brighter than a larger galaxy that forms stars slowly. This is especially true for galaxies filled with stars that are massive, metal-poor, and short-lived. They shine fiercely for a brief period before dying in dramatic explosions. So a galaxy can look developed without being old. It simply burns through its fuel fast. This is where the difference between bright and big matters. Older telescopes were biased toward detecting galaxies that were bright because they were physically large. Webb is detecting galaxies that are bright because they're efficient. The two categories can look similar from a distance, but their internal structures aren't the same. A compact 1,000 light-year wide galaxy can match the luminosity of a much larger modern galaxy if its star formation rate is high enough, and Webb is detecting several of these compact overachievers. Another reason these galaxies don't challenge the cosmological timeline is that redshift measurements depend on light, not appearance. When scientists say a galaxy sits at redshift 12, they're saying its light has been stretched by the expansion of the universe for about 13.5 billion years. That timestamp is rock solid. The light is as old as it is. What's surprising is not the timestamp, it's how much the galaxy managed to accomplish before that light left. This is the subtle point that gets lost online. You don't need more time to explain a bright young galaxy. You need higher efficiency. And efficiency is exactly what the early universe provided. Everything was compact. Everything was hotter. Everything moved faster. Gas didn't have to drift across enormous distances. It clumped easily. Gravity worked quickly. Collisions were frequent. Every process that drives star formation was turned up. So the earliest galaxies weren't impossible. They were simply operating in a more energetic environment than today's galaxies. Another key factor is mergers. Early halos didn't form in isolation. They formed in swarms. A single early galaxy could merge with several neighbors in just tens of millions of years. Each merger triggered a starburst. And starbursts create brightness spikes that make a galaxy look more mature than it is. In the early universe, mergers weren't rare events. They were the default mode of growth. Modern galaxies merge occasionally. Early galaxies merged constantly. This alone can account for a lot of Webb's surprising luminosities. But one of the biggest reasons early galaxies look older than expected has to do with feedback, radiation, winds, and explosions from massive stars. Feedback compresses some gas, blows out other gas, and reshapes the internal structure of a galaxy. If you compress gas in just the right way, you trigger fresh star formation. That means an early galaxy can experience repeated waves of stellar birth, each one adding layers to its appearance. Layers can fool the eye. A galaxy with 2 or 3 waves of early star formation can resemble a mature system even if its entire history is only 200 or 300 million years long. Then there's the black hole factor. A small black hole in a dense environment can grow rapidly. If it begins feeding early, it can add an active core that makes the galaxy appear older or more massive when viewed from afar. Webb has found hints of early black hole activity in galaxies that existed only a few hundred million years after the Big Bang. These black holes aren't enormous. They're modest by today's standards. But their presence adds complexity to systems that should, according to older expectations, still be simple. What makes this topic so confusing for the public is that old and complex are not tied together the way they are in everyday life. A newborn galaxy can be complex if the environment is extreme enough. A galaxy doesn't need eons to develop structure. It can develop structure as quickly as gas collapses and stars form, and that can happen extremely fast at high density. So even the galaxies that originally caused the biggest debates, ones labeled as redshift 12, 13, or even 17 candidates, haven't contradicted cosmology once the data matured. A few of the earliest record breakers turned out to be lower redshift after better spectroscopy. Others held up, and the ones that held up still fall comfortably within the timeline of the expanding universe. They're intense, but not impossible. This is where the deeper point becomes clear. Webb is refining the story of galaxy formation, not rewriting the story of cosmic origin. The Big Bang framework is still the only model that accounts for the expansion of the universe, the cosmic microwave background, the distribution of elements, and the large-scale structure. Webb's data fits neatly within that framework once you accept that the early universe was more productive than older simulations predicted. The thing that's shifting is our understanding of the early universe's behavior. Instead of a slow ramp-up from simplicity to complexity, we're seeing a universe that formed stars in rapid bursts, assembled galaxies quickly, and built early black holes faster than expected. But nothing in that picture violates the age of the universe. It just means gravity didn't waste any time getting to work. Another reason none of this breaks cosmology is that the age of the universe isn't inferred from galaxy properties. It's inferred from the expansion rate, the cosmic microwave background, and the entire framework of general relativity. Those aren't adjustable knobs, they're independently verified pieces of evidence that match the same age, about 13.8 billion years. A bright early galaxy doesn't rewrite that any more than finding a tall 6th grader rewrites human biology. The timeline stays the timeline. So why does the older than the Big Bang phrase stick so stubbornly to Webb's discoveries? Because the human brain has trouble with the idea that complexity doesn't require much time. We're used to the idea that building something, mountains, cities, civilizations, takes ages. But nature doesn't follow our pacing. Under the right conditions, it can build stars in a hurry, pile them into compact galaxies, merge those galaxies repeatedly, ignite new starbursts, and grow black holes, all in a cosmic blink. If anything, the lesson from Webb is that the universe had a jump start. The Big Bang gave it density. Density gave it speed. Speed gave it structure. And Webb is now showing the result of that speed with clarity we never had before. This is why astronomers aren't panicking over Webb's results. They're excited. It's like finally getting to watch the opening chapter of a story you've only ever read summaries of. Now we get to see how the earlier scenes actually played out. Messy, energetic, and faster than anticipated. The next big question, and the one scientists are now focusing on, is how this early efficiency transitioned into the more orderly universe we know today. How did these compact bursts grow into sprawling galaxies like the Milky Way? How did the chaotic early starbursts settle into long, steady cycles of star formation? And how did early black holes influence structures that eventually became the large-scale cosmic web? Those transitions are the next frontier. Webb is already starting to map them. And the more we see, the more it becomes clear that the early universe didn't break the rules. It simply used the rules to their fullest. When you zoom out from all the individual puzzles, early stars burning hot, black holes growing fast, galaxies forming in compact bursts, the big question becomes what all of this means for the next stage of cosmology. Webb isn't just adding details to the early universe, it's shifting how scientists think about the tempo and mechanics of cosmic evolution. And because cosmology connects everything from the first atoms to the large-scale structure of galaxies, the implications ripple outward. To understand those implications, it helps to think about what cosmology actually does. Cosmology sets the timeline. It gives you the broad strokes. When the universe expanded, when matter cooled, when structure formation began. It's not concerned with the small-scale physics of individual galaxies. That's astrophysics. But the two fields intersect in the early universe because the early universe is where tiny fluctuations in matter density grew into the first halos, and those halos eventually became the galaxies we can observe now. Before Webb, much of that earliest chapter wasn't visible. Cosmologists had a strong handle on the first fractions of a second after the Big Bang, and a strong handle on the cosmic microwave background 380,000 years later. But the window between 380,000 years and about 1 billion years after the Big Bang was murky. Telescopes like Hubble could only scratch the surface. That left a lot of freedom for models to fill in the gaps with reasonable assumptions. Webb is tightening those gaps. It's providing real snapshots, not predictions, of what galaxies and black holes looked like when the universe was only a few 100 million years old. And what those snapshots show is that the early buildup of structure was much more rapid and varied than most simulations predicted. That doesn't change the age of the universe. It changes the shape of the learning curve. In a sense, Webb is forcing cosmology to adjust to a universe that learned how to build galaxies faster than expected. This adjustment matters because structure formation depends on the behavior of dark matter. Dark matter forms the scaffolding that normal matter collapses into. If galaxies formed earlier or more efficiently, it could mean the earliest dark matter halos were denser or more numerous than some models assumed. It doesn't mean dark matter itself changed. It means the way dark matter clumped might have followed a slightly different pattern. And this is where Webb's data becomes extremely valuable. One of the things researchers are now analysing is the distribution of small halos at very high redshift. Before Webb, we could detect mainly the larger, brighter ones. Now, we're seeing smaller systems earlier. That helps refine models of how dark matter behaved at small scales. It also helps evaluate different variants of dark matter: cold, warm, self-interacting, ultralight, all of which predict slightly different early halo distributions. It's too early to say that Webb has ruled out any specific model, but the data is already placing tighter constraints on which versions of dark matter physics are compatible with the observed number of early galaxies. Another area where Webb's discoveries matter for cosmology is reionization, the era when the universe transitioned from neutral to ionized gas. For years, cosmologists used indirect clues to estimate when reionization happened and how patchy or uniform it was. Observations suggested reionization began around 400 million years after the Big Bang and was mostly complete by about 1 billion years. But the exact timeline and the specific sources responsible were debated. Webb is filling in that debate by showing that many early galaxies were bright enough in ultraviolet light to contribute significantly to reionization. It's also revealing that black holes played a role earlier than expected. And because Webb can catch faint galaxies, ones that telescopes like Hubble missed, it shows that the population responsible for reionization was larger and more varied. This helps cosmologists understand how fast the early universe went from being opaque to transparent. And that transparency affects how light from even earlier sources moves through space. One particularly interesting implication involves how early galaxies cluster. Large-scale clustering today tells us a lot about the universe's initial conditions. By observing how early galaxies are grouped, scientists can check whether the seeds of structure, the tiny density variations in the cosmic microwave background, grew into the right arrangements. Webb's early data hints that galaxies at high redshift are more clustered than expected. If that trend holds as more data comes in, it could mean that early halos formed in slightly denser environments. That doesn't break cosmology, but it might refine how cosmologists model the growth of density fluctuations. Another implication comes from the diversity of early galaxies. Some are compact and bright, others are diffuse and faint. Some show intense star formation. Others look unexpectedly quiet. This variety suggests early galaxy evolution didn't follow a single pathway. Instead, it followed multiple paths depending on the environment, merger history, and gas supply. That challenges the older idea of a typical early galaxy. Instead, the universe behaved like an experiment running many different trials simultaneously. Each trial produced a different outcome. This diversity is useful for cosmology because it helps identify which processes dominate under which conditions. But perhaps the biggest shift Webb is causing lies in how scientists think about the interplay between small-scale physics and large-scale structure. Before Webb, many simulations treated star formation and black hole feedback as background processes, important but not central to the large-scale picture. Now it's clear they're deeply intertwined. A single starburst in an early galaxy can expel gas into the surrounding medium, altering how nearby halos form. Meanwhile, energy from a feeding black hole can heat gas across tens of thousands of light years. In a universe where everything was close together, local events had global consequences. This interconnectedness matters because cosmology relies on simplifying assumptions. You can't simulate the entire universe star by star. You have to compress processes into simpler forms. Webb is showing which simplifications are still valid and which ones need to be upgraded. For example, many older models assumed early galaxies formed stars in a steady, continuous way. Webb shows they often formed stars in bursts, episodic, intense, and tightly clustered. That means large-scale simulations need to include more realistic, burst-driven feedback. Likewise, early black hole growth might have been more common than previously modelled. That has to be factored in. Another forward-looking consequence of Webb's discoveries involves gravitational waves. Several early galaxy models predicted that massive black holes didn't form until later in cosmic history. But if early galaxies already hosted black hole seeds, some from direct collapse, some from massive stars, that means black hole mergers were happening much earlier and more frequently. Future observatories like LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s, will listen for low-frequency gravitational waves from massive black hole mergers in the early universe. Webb's findings help narrow down when and where those signals should appear. Instead of expecting a gradual rise in merger activity, we may see intense early bursts. The interplay between Webb and gravitational wave astronomy is one of the most exciting aspects of the coming decade. Webb shows what early galaxies looked like. LISA will detect the vibrations from their black holes colliding. Combining those datasets will tell us not just how galaxies formed, but how the earliest black holes partnered, merged, and reshaped their environments. Another future implication lies in the search for population 3 stars, the first metal-free stars. Webb hasn't found direct evidence of them yet, but it has found conditions where they could have existed. It's also detected galaxies with spectral signatures that are very close to what you'd expect if population 3 stars recently lived there. That pushes researchers to refine their predictions. If we know what chemical footprints to expect, we can design better search strategies. And if Webb eventually does find direct evidence of these stars, or even their supernova, it would be one of the biggest discoveries in modern cosmology. It would link the theoretical first stars with actual observational data. Another long-term consequence is how scientists think about the cosmic Middle Ages, the billion-year period after the first burst of formation but before modern galaxies settled into stable shapes. Webb is beginning to map this transition. It's showing how early starbursts faded, how gas settled into disks, and how black hole feedback eventually stabilized star formation. These transitions matter for cosmology because they reveal how the universe went from compact, chaotic systems to the structured cosmic web we see today. If early galaxies influence their surroundings more than expected, the transition from chaos to order may have happened sooner, or in different ways than previously thought. And finally, there's a philosophical implication. Not the kind that tries to replace cosmology, but the kind that encourages scientists to question old assumptions. Webb has shown that the universe often takes the fastest available path to complexity. It doesn't waste time, it doesn't build slowly when it can build quickly. That mindset affects how cosmologists think about everything from early chemical enrichment to large-scale structure formation. It encourages them to consider more energetic scenarios, wider ranges of star formation rates, and more diverse early galaxy populations. In other words, it pushes the field toward creativity grounded in evidence. None of Webb's discoveries weaken the Big Bang model. Instead, they enrich it. They take a timeline that was broadly understood and fill in the missing chapters with detail, surprise, and nuance. Cosmology's foundation remains solid. What's changing is the story of how the universe grew from simplicity to complexity, and how quickly it made that leap. It's easy to see a headline like "James Webb just found something older than the Big Bang" and feel like something fundamental must be broken. If something is older than the Big Bang, that would mean it existed before space, before time, before the physics that describe everything around us. But what Webb is actually showing us is more grounded than that, and honestly, more interesting. The Big Bang isn't a moment when stuff exploded, it's the moment when the clock started. So when people say Webb found something older, what they usually mean is that it found something earlier than expected, something that formed surprisingly fast, or surprisingly bright, in a universe that was still a newborn. Webb detects light that traveled more than 13 billion years to reach us. That light carries snapshots from a time when the universe was only a few 100 million years old, and some of those snapshots don't fit neatly into earlier models. So the real story here isn't that Webb is breaking the Big Bang, it's that it's revealing just how fast the early universe went from simple to complex. The Big Bang model sits at the foundation of modern cosmology, and it earned that place by matching decades of evidence. The expansion of space, the cosmic microwave background, and the abundance of the earliest elements all point to a beginning 13.8 billion years ago. That doesn't mean every detail was nailed down. There were gaps, especially between the formation of the first atoms and the rise of the first galaxies. Before Webb, telescopes could only glimpse the edge of that era. Simulations filled in the rest with assumptions based on what seemed reasonable. When Webb looked deeper, it uncovered places where those assumptions were too conservative. The age of the universe didn't change, the complexity of the early universe did. That's a huge difference. It shifts the growth curve without changing the timeline. One reason this causes confusion is that old in cosmology doesn't work like old in everyday life. A galaxy doesn't have to be ancient to look bright or large. It just has to form stars quickly, merge frequently, or collapse efficiently. In the early universe, those conditions were common. Everything was closer together. Gas cooled quickly. Mergers happened constantly. Black holes had no trouble finding fuel. If you take a small galaxy and load it with hundreds of solar masses of new stars every year, it can look mature in a few tens of millions of years. In a universe that's only a few 100 million years old, that's fast enough to confuse people who assume brightness equals age. Webb keeps finding galaxies like that, not ancient ones, just efficient ones. The telescope also finds compact galaxies that pack enormous brightness into small volumes. Some are only a fraction of the Milky Way's size, but emit light at levels that rival much larger systems. Compactness doesn't imply age, it implies density. Dense systems shine brightly because their massive stars burn hot and fast. They live short lives, but they dominate the light. So a young, compact galaxy filled with massive stars can outshine a larger galaxy full of older, quieter stars. When Webb catches one of these early overachievers, it's easy for headlines to turn unexpectedly bright into older than the Big Bang, even though nothing about it violates the timeline. To understand why these discoveries matter, you have to look at the early universe itself. The period between the cosmic microwave background and the first billion years has always been a missing chapter. Cosmologists knew the broad strokes. Tiny fluctuations in density eventually became the first gravitational wells, and those wells became the first halos of dark matter and gas. But the exact timing, speed, and pathways of early structure formation were largely based on models. Webb finally gives us real snapshots of that era, and those snapshots show a universe that wasn't slow or delicate. It was quick, crowded, and efficient. Matter collapsed faster. Gas cooled quickly. Mergers were frequent. Black holes fed aggressively. All of this produced galaxies that looked surprisingly mature despite being extremely young. This matters because it tells cosmologists where their models were too cautious. Many older simulations assumed early galaxies formed stars steadily. Webb shows they formed stars in bursts, short, intense episodes that produced huge amounts of ultraviolet light. That ultraviolet light played a major role in rhionization, the era when the universe's gas went from neutral to ionized. Webb's data shows that early galaxies contributed far more to rhionization than expected. It also shows that black holes were active earlier than models predicted. Both of these observations help tighten the timeline of how the universe became transparent and how light from even earlier sources traveled through space. The distribution of early galaxies also reveals how dark matter behaved in the first few 100 million years. dark matter forms the scaffolding for normal matter. If early galaxies appeared in greater numbers or in denser clusters than simulations expected, that tells cosmologists something about dark matter's early structure. Webb's data hints that early halos might have been slightly denser or more varied in size than some models assumed. This doesn't undermine the idea of dark matter. It just refines the details of how it clumped in the beginning. One of the biggest impacts of Webb's discoveries is how they change the relationship between small-scale and large-scale processes. In older models, galaxy-level processes like star formation, supernova explosions, and black hole feedback were often treated as local events with limited influence. Webb shows that in the early universe, those events had a much bigger reach. Gas outflows from early starbursts could reshape the environments of nearby forming galaxies. Energy from feeding black holes could heat large surrounding regions, influencing how easily gas collapsed into new stars. When everything in the universe is close together, nothing stays isolated. That interconnectedness forces cosmologists to rethink how they combine small-scale astrophysics with large-scale cosmic evolution. Webb's discoveries also have big implications for future observatories. If black holes formed earlier than expected, that means mergers happened earlier too. That sets the stage for upcoming missions like LISA, which will detect low-frequency gravitational waves from massive black hole mergers in the early universe. Webb is essentially giving us the map of where those early mergers might have happened. When LISA launches, scientists will combine Webb's snapshots with gravitational wave signals to create a more complete story of how the universe built its first massive structures. Another area where Webb is pushing the field forward is in the search for population 3 stars, the universe's first metal-free stars. These stars have never been observed directly, but Webb is finding galaxies with chemical signatures that suggest these stars may have recently existed there. If Webb eventually catches one of their supernovae or finds a galaxy with a clear population 3 imprint, it would be one of the most important discoveries in cosmology. It would connect decades of theoretical predictions with direct observational evidence. And all these discoveries point to a universe that didn't waste time. It moved from simplicity to complexity far faster than anyone expected. That doesn't change when the universe began. It changes how much happened in the first few 100 million years. For cosmology, that's not a crisis. It's a gift. It means the missing chapter is finally being filled in, not with speculation, but with real observations. Webb isn't rewriting the origin story. It's adding details that make the story richer, sharper, and more accurate. And this brings us back to that headline about something older than the Big Bang. Nothing Webb has found breaks the timeline. Nothing escapes the rules of relativity. Nothing predates the expansion of space. What Webb is doing is revealing that the universe was more capable, more dynamic, and more efficient than older models accounted for. These discoveries don't weaken the Big Bang model. They strengthen it by showing how much room there was for complexity within its framework. As more data arrives, models will keep evolving. That's the point of science. Every round of observations tightens the picture. Every improvement in technology lets us test the assumptions that came before. And Webb is simply the most powerful tool we've ever used to study the earliest cosmic era. The surprises it reveals aren't signs of failure. They're signs that cosmology is entering a new phase, one where the first billion years of the universe finally come into focus. Watch the next video.